The universe is vast, puzzling, and sometimes even overwhelming. Its beauty and scale are beyond anything we can fully grasp. It is the birthplace of everything we know, our starting point, and a place we are always eager to explore. Yet the universe is filled with unanswered questions and strange phenomena. In this video, we'll explore a question that has puzzled us all for centuries. What is beyond everything we can observe? Imagine a vast ocean stretching far beyond what the eye can see. Now, imagine each drop of water in that ocean representing a single star. That's how immense our universe truly is. In our galaxy, the Milky Way, there are at least 100 billion stars, but that's just one galaxy. Astronomers estimate that in the visible universe, there are around 2 trillion galaxies, both large and small. If we multiply the number of stars in each galaxy by that number, we arrive at an almost incomprehensible figure, roughly 200 billion trillion stars. Take a moment to grasp the enormity of that number, and that's just the stars. We already know that most stars have planets orbiting them, and many of those planets are similar to Earth. With such an unfathomably large number of planets out there, the question arises, are we truly alone in the universe? Yet some people still claim with certainty that we are the only intelligent life in existence. But does that even make sense? Among the thousands of exoplanets discovered so far, many share characteristics with Earth, suggesting they might support life. Could it really be that not a single one of these countless planets harbors life? Or is there something stopping us from knowing the truth? Today, we're diving deep into this cosmic mystery. Fasten your seatbelts, because what you're about to learn might leave you amazed, or even a little unsettled. We will explore why finding fossils of complex life on another planet might actually be terrifying news, and we'll discuss theories that suggest we could be living inside a massive simulation or even a cosmic nature reserve. Stick around, because the answers to these questions might just change the way you see the universe. It all began with a casual lunchtime conversation in the year 1950. Several renowned physicists, including Enrico Fermi, an American scientist of Italian descent, were gathered at a university. Among them were Emil Konopinski, Edward Teller, and Herbert York. Their discussion started with reports of unidentified flying objects, a topic that was making headlines at the time. As the conversation shifted, they began to speculate on whether physical objects could move faster than the speed of light. That's when Fermi posed a simple yet groundbreaking question. Where is everyone? He was referring to extraterrestrial civilizations. If the universe is so vast and filled with stars and planets, why haven't we seen any clear signs of intelligent life? Why haven't aliens made contact with us? At that point, humanity had already been broadcasting radio and television signals into space for about 100 years. Scientists had even sent messages into the cosmos, hoping to reach intelligent extraterrestrials. Thousands of people worldwide had joined efforts like the SETI, Search for Extraterrestrial Intelligence program, analyzing signals from space. But so far, all we've received in return is silence. Fermi, always the scientist, decided to approach the question mathematically. He started multiplying probabilities. The chances of stars having planets, the likelihood of life forming, the probability of intelligent civilizations developing, and so on. Based on his rough calculations, alien civilizations should have visited Earth long ago, many times. So why haven't they? Fermi proposed several possibilities. Maybe interstellar travel is simply impossible. Maybe it's technically possible but not worth the effort. Or perhaps civilizations don't survive long enough to make contact. But at the time, Fermi didn't know about wormholes, hypothetical shortcuts through space-time. If he had, he might have joked that every home on Earth already had a hidden wormhole, with an alien watching us from the other side. Could it be that we're being observed right now, without even realizing it? Could advanced extraterrestrials be keeping their presence hidden? Some scientists today seriously consider the possibility of wormholes existing. If we advance our technology just a little more, we might even learn how to create them. But that still brings us back to the original question, where is everybody? About 10 years after Fermi's famous question, an astronomer named Frank Drake attempted to put the mystery into numbers. In the year 1961, he introduced what is now called the Drake equation. It's a mathematical formula designed to estimate the number of extraterrestrial civilizations in our galaxy that humanity might have a chance to communicate with. Drake's equation takes multiple factors into account. How often new stars are formed? How many of those stars have planets? How many planets could support life? How many actually develop intelligent life? And how many advanced civilizations might be sending signals into space? Of course, we don't yet have solid numbers for most of these factors, but that wasn't the point. Drake didn't create the equation to solve the mystery. He created it to keep the conversation going, and it worked. For over 70 years, scientists, philosophers, and enthusiasts have debated the implications of the Fermi paradox and the great silence of the universe. So, we ask again, where is everyone? Why haven't we heard a single confirmed signal from another civilization? Why haven't they heard us? Could it be that we are truly alone? Or is there a much larger truth that we simply aren't ready to face? One of the most debated theories about why we haven't found intelligent alien life is called the Great Filter. This idea was introduced by Robin D. Hanson, a researcher at the Future of Humanity Institute at Oxford University. The theory suggests that there is a nearly impossible barrier, either in the past or in the future, that prevents civilizations from advancing beyond a certain point. In simple terms, if human evolution up to now has been relatively easy, then the worst may still be ahead for us. At first, this might not sound obvious, but think of it like this. Have you ever heard the joke, "I intend to live forever, so far, so good"? It's funny when applied to an individual, but not so amusing when you consider it in terms of humanity as a whole. Hansen started questioning why, despite the high probability of advanced alien civilizations existing, we haven't seen any sign of them. He proposed that there might be an unknown factor that makes it extremely difficult for life to develop to the point where it can leave a noticeable mark on the universe. If this is true, then the average lifespan of a civilization might be too short for it to ever overlap with another one in the same region of space. A good way to imagine this is by thinking of ripples in a pond. If you throw a small stone into the water every now and then, the ripples will quickly disappear before they have a chance to meet. Now, imagine space as an enormous pond, stretching across billions of light years and billions of years in time. One civilization might just be learning how to make fire while another, far away, has already destroyed itself in a nuclear war. The odds of two civilizations existing at the same time and in the same area are incredibly low. Just think about human history. How many times have we been on the brink of destruction? And we don't have to look too far back. Do you remember the year 2020? The global pandemic showed us how fragile our civilization really is. Hansen outlined 9 major steps that any civilization must go through to reach an advanced space-exploring stage. The formation of a solar system with planets that can support life. The appearance of self-replicating molecules such as RNA on one of those planets. The development of simple single-celled organisms, prokaryotes. The evolution of more complex single-celled life forms, eukaryotes. The emergence of sexual reproduction. The evolution of multicellular organisms. The rise of intelligent beings capable of using tools. The development of a technologically advanced civilization. The expansion of that civilization into space. According to the Great Filter hypothesis, at least one of these steps is almost impossible to achieve. If the first 8 steps were easy, then we would expect to see countless other civilizations at our level. But we don't. That suggests that step 9, spreading across space, is the hardest one to reach. And if that's true, something might be stopping civilizations from surviving long enough to take that final step. What could that be? It could be nuclear war, a deadly epidemic, a massive asteroid impact, the collapse of natural resources, or even something we don't yet understand. The reality is, the Great Filter might still be in our future. Now let's imagine we found proof of life on a nearby planet. At first, this might seem like amazing news. If life can start on Earth and another planet, then maybe it's common throughout the universe. But what if we only found simple bacteria on Mars, or beneath the icy surface of Jupiter's moon Europa? That would mean the Great Filter comes after the point where life begins, meaning it could still be ahead of us. Now, imagine we discovered fossils of complex alien creatures, perhaps something like fish or even larger animals. That would be an even bigger discovery, but also a terrifying one. It would suggest that life easily reaches the multicellular stage, yet never survives long enough to become an advanced civilization. That would mean the Great Filter is almost certainly in our future. As Nick Bostrom, another philosopher from Oxford, once said, "That would be the worst news ever to make the headlines." Why? Because it would suggest that while life may be common in the universe, no civilization has ever survived long enough to become interstellar. If that's the case, why should we believe that we'll be the first? Now picture a scenario where scientists start discovering alien fossils all over the universe. Exciting, right? But then we realize something strange. There are no signs of intelligent civilizations, no signals, no spacecraft, nothing but ruins of extinct life. That would mean something has wiped out every civilization before they could reach the stars. And if that's true, what are the chances we can avoid the same fate? But before we panic, let's remember, this is all just a theory, and humans are known for their resilience, creativity, and ability to find solutions to impossible problems. Many scientists have proposed alternative explanations for why we haven't found aliens yet. Some of them are logical, some are bizarre, but all of them remind us that the universe is still full of mysteries waiting to be solved. To truly understand some of the most fascinating and bizarre ideas about the universe, we must temporarily set aside our common sense. This may sound counterintuitive, but in reality there is nothing unscientific about it. What we often call common sense is merely a collection of beliefs shaped by the time and society we live in. What seems logical today might have been considered absurd centuries ago. A perfect example of this is the story of Giordano Bruno, an Italian philosopher who lived in the 16th century. He dared to suggest that the universe was infinite and that countless other worlds existed beyond our own. His ideas were considered so dangerous that he was executed for them. In his time, the people who condemned him believed they were acting rationally. This shows how the boundaries of common sense shift over time. With this in mind, let's explore some of the most extraordinary ideas about the universe. Ideas that may seem strange now, but could one day change the way we see everything. One of the most thought-provoking theories about why we have not yet encountered extraterrestrial life comes from Liu Cixin, a well-known Chinese science fiction writer. He introduced the idea of the dark forest hypothesis to explain the Fermi paradox, the contradiction between the high probability of alien life and the complete lack of evidence for it. According to this theory, the universe operates under a brutal rule of survival, much like the animal kingdom on Earth. If a civilization becomes advanced enough to explore space, it quickly realizes that announcing its existence could be incredibly dangerous. Just like in a dense, dark forest, where every creature is both a hunter and potential prey, civilizations must remain silent to avoid attracting the attention of more powerful and hostile beings. Any young, naive civilization that openly broadcasts its presence, like a lost traveler making noise in a predator-filled jungle, risks immediate destruction before it even realizes the danger. This concept aligns closely with the warnings given by the legendary physicist Stephen Hawking. He cautioned against sending signals into deep space, fearing that if an advanced extraterrestrial civilization detected us, the consequences could be catastrophic. He compared this situation to what happened when European explorers arrived in the Americas, an encounter that led to the destruction of native civilizations. But what if Hawking was only half right? What if intelligent aliens have already found us but have chosen to observe rather than attack? Imagine a vast nature reserve, carefully protected by unseen guardians. Now apply this idea to the universe. What if our planet, or even the entire galaxy, is part of an intergalactic nature reserve, shielded from contact with advanced civilizations? To understand this, let's look at Serengeti National Park in Tanzania. This vast protected area spans nearly 15,000 square kilometers and is home to over 3 million large animals and nearly 500 species of birds. Every year, tourists travel from all over the world to observe the magnificent wildlife. Yet most of the animals within the park have no awareness of humans. They live their lives, oblivious to the fact that their world is carefully managed by creatures far beyond their understanding. Now, imagine that we are like those animals, and an advanced alien species has placed us in a cosmic equivalent of the Serengeti. They monitor us, enforce certain boundaries, and prevent direct contact. To us, they are invisible, just as the concept of human civilization is meaningless to a wildebeest or a zebra. If this is true, Then when we ask, where is everyone? We might simply be too limited in our perception to see the answer. Even more intriguingly, what if we are as insignificant to advanced extraterrestrials as ants or butterflies are to us? Even more intriguingly, what if we are as insignificant to advanced extraterrestrials as ants or butterflies are to us? When an ant crawls across the ground, it has no concept of the human world, skyscrapers, airplanes, or the internet. Similarly, an alien species thousands or millions of years ahead of us might exist in a way that is simply beyond our comprehension. To them, we might not be worth interacting with at all. If the idea of an intergalactic nature reserve sounds incredible, the next theory pushes the boundaries even further. Nick Bostrom, a Swedish philosopher and professor at Oxford University, proposed one of the most mind-bending ideas of all time, the simulation hypothesis. Published in 2003, Bostrom's theory suggests that if a civilization becomes advanced enough, it will develop computers powerful enough to create highly realistic simulations of reality. These simulations could become so sophisticated that the beings inside them, like us, would be unaware that they are not in the real world. Think about how video games have evolved over the past few decades. The first computer games were simple, pixelated graphics, but today's games feature stunningly realistic environments. If technology continues to improve, it is not unreasonable to imagine that one day a computer simulation could be indistinguishable from reality. Now, take that idea a step further. What if we are already living inside one of these simulations? If every advanced civilization eventually creates virtual worlds, then the number of simulated beings could far outnumber those in the original reality. This means that the odds of us living in a simulation might be greater than the odds of us existing in a base reality. And if we are in a simulation, then the reason we do not see intelligent alien civilizations might be because they are simply not part of the program, or perhaps they exist in another layer of the simulation that we cannot access. These theories are fascinating, and some of them might even be true. But there is one possibility that is so simple and so terrifying that we rarely want to say it out loud. What if there is no great filter, no cosmic zoo, and no simulation? What if the reason we do not hear from other civilizations is that we are the only intelligent life in the universe? This is the most unsettling answer to the Fermi paradox because it strips away all hope of ever finding others like us. If we are truly alone, then the responsibility of shaping the future of intelligence in the universe rests solely on our shoulders. There is no wiser, older civilization to guide us. There is no one to save us if we destroy ourselves. This realization makes the silence of the universe not just eerie but deeply unsettling. If we are the only ones, then every decision we make about our planet, our technology, and our survival carries an unimaginable weight. One of the most thought-provoking theories about the universe and extraterrestrial life is called the dark forest hypothesis. It was introduced by the Chinese science fiction writer Liu Cixin as a way to explain the Fermi paradox, the puzzling contradiction between the high probability of alien civilizations existing and our complete lack of evidence for them. The theory suggests that intelligent life in the universe is locked in an endless struggle for survival. Much like animals in the wild, civilizations must compete with one another, and the strongest ones dominate. Because of this, any intelligent species that reaches an advanced stage of development will go to great lengths to hide its existence, fearing that revealing itself might invite destruction. Imagine a lone traveler walking through a dense and silent forest at night. It may seem like the traveler is alone, but hidden in the darkness, predators are watching. If the traveler makes too much noise, he will reveal his presence, and before he even understands what's happening, he will be gone. According to the dark forest theory, civilizations that make their presence known in the cosmos could be like that unlucky traveler. The renowned physicist Stephen Hawking voiced similar concerns. He warned that broadcasting signals into space, hoping to attract the attention of distant civilizations, might not be the wisest move. If a highly advanced civilization were to detect our signals, its response might not be friendly. History offers a grim reminder. When European explorers arrived in the Americas, their vastly superior technology led to the downfall of many native civilizations. If the same pattern holds true on an intergalactic scale, Earth could face a similar fate. But what if advanced civilizations already know we exist? What if they are simply watching us rather than seeking to destroy us? To understand this idea, let's take a look at the Serengeti National Park in Tanzania. This vast wildlife reserve, spanning nearly 15,000 square kilometers, is home to 3 million large animals and nearly 500 species of birds. Every year, massive herds of wildebeest, gazelles, and zebras migrate across its plains, traveling approximately 3,000 kilometers in search of food and water. Although thousands of tourists visit the Serengeti each year, most of the wild animals have never encountered a human. Even fewer have ever seen the people who originally established the park and set its boundaries. To these animals, humans are an unknown force, almost like invisible gods shaping their world. They have no idea that they live in a designated wildlife reserve. They don't understand the concept of property lines, conservation laws, or the powerful beings managing their environment from afar. What if we are like those animals? What if our world, our entire universe, is nothing more than a cosmic nature reserve, carefully maintained by an advanced civilization? If such beings exist, they may not even need to interact with us directly. To them, we might be as insignificant as ants or butterflies are to us. If an ant could think, it might wonder why it never sees any large creatures controlling the world around it. But humans do exist. We just operate on a scale far beyond an ant's ability to comprehend. Now, let's consider an even more astonishing possibility. The simulation hypothesis is one of the most controversial ideas in modern philosophy and science. It was famously developed by Nick Bostrom, a Swedish philosopher and professor at Oxford University. In a groundbreaking paper published in the year 2003, Bostrom argued that if humans continue to develop advanced technology, future generations will likely create highly realistic computer simulations of the past. If these simulations become advanced enough, the people inside them may not even realize they are living in an artificial world. This raises an unsettling question. What if we are already inside one of those simulations? Think about how far video game technology has come. Each year, games become more detailed, more realistic, and more immersive. If technology continues to advance at this pace, it is not far-fetched to imagine that one day people could create simulated worlds so perfect that the inhabitants would be unaware they were living in a computer-generated reality. If this is possible, then logically, it is far more likely that we are inside such a simulation right now than that we are living in the real universe. If that is the case, the vast emptiness of space, the so-called great silence that scientists struggle to explain, might not be real at all. It could simply be a limitation of the simulation we exist in, like the boundaries of a video game. The stars and galaxies we see in the night sky could be nothing more than a programmed illusion placed there to make our world feel vast and mysterious. Of course, these are just theories, some more bizarre than others. But even the wildest hypotheses may turn out to be more plausible than the simplest and most terrifying explanation of all. What if we are completely alone? The Fermi paradox asks why we see no signs of intelligent alien life despite the vastness of the universe. One of the most straightforward answers is that there is no one else out there, that humanity is the only intelligent species in existence. If this is true, then all of our dreams of making contact with extraterrestrial civilizations are nothing more than wishful thinking. Many scientists, including the famous Carl Sagan and Frank Drake, have spent their lives searching for alien signals, believing that Earth is just one of countless planets orbiting an average star in an ordinary galaxy. But despite all our efforts, the silence remains. If life were common, surely we would have found evidence of it by now. And that leads to the most chilling possibility of all. Perhaps there is no great filter, no dark forest, no cosmic zookeeper, and no simulation. Perhaps we are simply the first and possibly the last intelligent beings to ever exist. For a long time, many scientists believed in something called the mediocrity principle. This idea suggests that Earth and humanity are nothing special. We're just another planet orbiting an average star in a universe full of countless worlds, many of which should also have life. If that were true, then we should have already found evidence of other civilizations, or at least some form of alien life. But where is everyone? At first, the mediocrity principle seemed to make sense. It became a part of popular science discussions, and for years very few people questioned it. However, as scientists made new discoveries, doubts started to creep in. If Earth and life itself were so ordinary, why haven't we seen signs of aliens? The more we studied our own planet and its history, the more we realized just how many rare and extraordinary conditions were needed for complex life to survive. And that brings us to an alternative idea, one that is even more unsettling. The rare Earth hypothesis suggests that instead of life being common in the universe, it might actually be incredibly rare. In fact, it could be so rare that Earth might be one of the only planets to have ever developed complex life. If this is true, it means that we are almost completely alone in an unimaginably vast universe. This idea can feel deeply unsettling, even frightening, as it suggests that intelligent life may be a nearly impossible accident, a miracle that may never be repeated anywhere else. The rare Earth hypothesis was explored in detail by scientists Peter D. Ward and Donald Brownlee in their book Rare Earth: Why Complex Life is Uncommon in the Universe. They argue that life, especially intelligent life, can only exist under a unique set of extremely rare conditions. Even a slight change in those conditions could prevent life from developing at all. Most people have heard of the Goldilocks zone, also called the habitable zone. This is the region around a star where conditions are just right for liquid water to exist on a planet's surface, neither too hot nor too cold. Many assume that if a planet exists in this zone, life is almost guaranteed to develop. But in reality, the situation is far more complex. Earth's ability to support life isn't just about being in the right distance from the Sun. Our orbit is also nearly perfect. It's almost a circle. This means that throughout the year, our planet stays at a stable temperature, never drifting too close or too far from the Sun. If our orbit were more elongated, we would experience extreme seasonal changes, making survival much harder. But that's just the beginning. Even if a planet is in the Goldilocks zone, many other conditions must also be met. Surprisingly, the entire galaxy also has its own habitable zone, and Earth happens to be located in the perfect spot. The Milky Way galaxy is vast and filled with dangers. It takes our solar system about 235 million years to make one full orbit around the center of the galaxy. Since the first oceans formed on Earth, our planet has completed this journey about 17 times. Since the first simple life forms appeared, we've made this trip about 15 times. And since the rise of the first multicellular organisms, we've traveled around the galaxy about 7 times. This journey has not been smooth or easy. The space between stars is not just empty, it's filled with deadly threats. Along the way, our solar system has encountered many cosmic hazards that could have wiped out life entirely. One of the biggest dangers is our location in the galaxy. Most of the Milky Way is actually a dead zone where complex life cannot survive. The closer a star is to the center of the galaxy, the more it is exposed to intense radiation from black holes, neutron stars, and powerful gamma-ray bursts. These cosmic phenomena release deadly energy that can sterilize planets, wiping out any potential life. Supernova explosions, massive star deaths, are another threat. These events release incredible amounts of energy, sometimes destroying everything within many light years. A planet too close to a supernova could have its atmosphere completely stripped away, making life impossible. Even gravitational disturbances pose a risk. If a planet is located too close to the center of the galaxy, the intense gravitational forces from passing stars or even rogue black holes could disrupt its orbit. This would create chaos, potentially throwing planets out of the habitable zone or even out of their solar systems entirely. On the other hand, being too far from the center of the galaxy is also problematic. Stars located in the galaxy's outer edges have very low amounts of heavy elements, materials necessary to form Earth-like planets. Without these elements, planets might exist, but they would likely be barren and lifeless. Recent studies suggest that the galactic habitable zone, the region where conditions are just right for life, extends between 7,000 and 9,000 parsecs from the center of the Milky Way. This is approximately 22,800,000 to 29,300,000 light-years from the galaxy's core. Shockingly, only about 10% of all stars in the Milky Way exist in this narrow band, and among those, only a fraction have planets suitable for complex life. Earth is not just in this habitable zone, it also orbits the galaxy in a nearly perfect circular path. This means that for billions of years, our solar system has remained in the ideal location without drifting too close to dangerous regions or moving too far into the lifeless outskirts. Even beyond the habitable zone, our entire galaxy is remarkably special. The Milky Way has remained stable for an extraordinarily long time. For about 10 billion years, it has not experienced a major collision with another galaxy. This is incredibly rare. Most galaxies frequently crash into one another, causing massive chaos that can destroy solar systems and disrupt the conditions needed for life. To put this into perspective, the universe itself is only about 13 billion years old. For about 10 billion years, it has not experienced a major collision with another galaxy. This is incredibly rare. Most galaxies frequently crash into one another, causing massive chaos that can destroy solar systems and disrupt the conditions needed for life. To put this into perspective, the universe itself is only about 13 billion years old. That means our galaxy has been unusually peaceful for most of its existence. Only about 7% of galaxies in the universe share this level of stability. However, this stability won't last forever. The Milky Way is currently moving toward its closest neighbor, the Andromeda Galaxy, at an astonishing speed. In about 4 billion years, the two galaxies will collide. This event could be catastrophic, potentially disrupting star systems and even destroying any remaining civilizations. If humanity is still around by then, we will face a choice: either become an interstellar civilization capable of surviving beyond our home galaxy, or risk being wiped out by the chaos of the collision. If we fail to expand into space in the next few billion years, we may be doomed. When we consider all these factors, the habitable zones, the rare conditions, and the incredible stability Earth has enjoyed, it becomes clear why we may not have found alien life. It is not because life is common and we simply haven't looked hard enough. It may be because life, especially intelligent life, is so unbelievably rare that it barely exists at all. This realization is both humbling and terrifying. If the rare Earth hypothesis is correct, we may be one of the only intelligent species in the universe. That means the responsibility of preserving and expanding life beyond Earth falls entirely on us. So, while the mediocrity principle once suggested that life was everywhere, the evidence now seems to tell a different story. We are not just another planet. We are an extraordinary exception in an unimaginably vast, empty universe. Let's move on to our next point. When we look up at the vast night sky, we often admire the countless shining dots scattered across the darkness. It's easy to assume that many of them might be just like our sun, varying only in size and brightness. But that assumption couldn't be further from the truth. Scientists estimate that at least half of all the stars in our Milky Way galaxy are not solitary like our sun, but are actually part of binary or even multiple star systems. Take, for example, the North Star, Polaris. Most people think it's a single bright star guiding travelers, but in reality, it's part of a system made up of 3 stars, all bound together in an intricate cosmic dance, each affecting the movement of the others in ways that are difficult to predict. We often see in science fiction movies breathtaking scenes of alien worlds with 2 or even 3 suns setting over the horizon, bathing the landscape in strange, colorful light. It's a mesmerizing image, but in reality, planets in such systems would face enormous challenges. For a planet to support life, it needs a stable orbit within what scientists call the habitable zone, the region around a star where temperatures allow liquid water to exist. However, in a system with multiple stars, the gravitational pull from each star would make it nearly impossible for a planet to maintain a stable orbit for billions of years. Instead of a steady environment, such a planet would experience wild temperature swings and unpredictable shifts in climate, making it an incredibly hostile place for life as we know it. But we don't even need to venture into multi-star systems to see how unique our sun is. Even though it may seem like an ordinary star, it possesses characteristics that are surprisingly rare in the universe. Our sun is remarkably stable. Its brightness fluctuates by only 0.1% over time. This is a crucial factor for life because even slight variations in a star's energy output could cause catastrophic climate changes on an orbiting planet. Although astronomers have discovered many stars classified as being in the same category as our sun, not a single one has been found to match its combination of mass, brightness, age, temperature, and composition. Each of these factors plays a vital role in determining whether a planet orbiting a star has any chance of sustaining life. But our sun's stability isn't the only unusual feature that makes life possible. The very structure of our solar system is highly uncharacteristic. For one, the gas giants, Jupiter and Saturn, are located in just the right positions to act as protective guardians. Their immense gravity helps shield the inner rocky planets from constant asteroid and comet impacts. Without these giant planets acting as cosmic bodyguards, Earth would have been bombarded far more frequently by devastating space debris, potentially preventing life from ever gaining a foothold. Then there's our moon, which plays a critical role in stabilizing Earth's tilt. This stability is crucial because it keeps our seasons consistent over long periods of time. If the moon were absent or significantly smaller, Earth's axis would wobble chaotically, leading to unpredictable climate shifts that could have made complex life impossible. Even when we consider all of these rare factors together, they still pale in comparison to the greatest mystery of all, the origin of life itself. One popular scientific idea, known as the panspermia hypothesis, suggests that life may have arrived on Earth via a comet or asteroid. But even if we assume that life was delivered to our planet already in a primitive form, the process of evolution that followed presents its own mind-boggling challenges. Life on Earth has endured some of the most extreme conditions imaginable. It survived two massive global ice ages, one about 2 billion and 200 million years ago, and another about 635 million years ago. These events, known as snowball Earth periods, should have been devastating. Yet ironically, they may have actually helped life evolve. The first global freeze triggered the rise of photosynthetic microorganisms, which absorbed greenhouse gases from the atmosphere and led to the accumulation of oxygen, a critical ingredient for complex life. Then, after the second deep freeze, something incredible happened: the Cambrian explosion. This event, which took place about 540 million years ago, saw an unprecedented burst of life forms appearing, leading to the evolution of almost all major groups of animals that exist today. It was during this period that the first primitive brains emerged. It's important to understand that Earth's difficult history, including ice ages and mass extinctions, may have been essential for the development of intelligent life. If we were to find a hypothetical paradise planet with conditions that remained stable and perfect for billions of years, chances are it wouldn't have evolved intelligent life at all. Why? Because life only evolves complexity when it's forced to solve difficult problems. If an environment provides everything easily, there's no need for organisms to develop intelligence, adaptability, or complex structures. In such a scenario, life might remain at the level of simple bacteria or algae, never advancing into more complex creatures. It may sound harsh, but struggle and adversity are necessary for evolution. Just as day and night, summer and winter, predator and prey exist in a delicate balance, life thrives when it is challenged. If conditions are too easy, there's no pressure to adapt. If conditions are too extreme, life may not survive at all. Evolution requires just the right balance of both stability and challenge. Now, consider this. Even if all the right conditions align perfectly, the right kind of star, a planet in the habitable zone, a stabilizing moon, a protective arrangement of gas giants, and the presence of water and atmosphere, it still doesn't mean that life will appear. The foundation of life as we know it depends on the existence of a self-replicating molecule, something capable of copying itself and passing on information. This is the first brick of life. But how did this first replicator come into existence? Modern science has tried to simulate the spontaneous emergence of this crucial molecule, but the results are astonishing. One of the most respected scientists in this field, Russian-American evolutionary biologist Eugene Koonin, has calculated the probability of the first self-replicating molecule appearing by pure chance. The number he arrived at is staggering, 1 in 10 to the power of 118. To put that into perspective, the total number of atoms in the entire observable universe is estimated to be around 10 to the power of 80. That means the odds of life arising spontaneously are so unbelievably small that they are beyond human comprehension. Faced with such impossible odds, even brilliant scientists like Koonin have been forced to consider alternative explanations. One such idea is the multiverse hypothesis, which suggests that our universe is just one of countless universes, each with its own physical laws and conditions. If there are an infinite number of universes, then maybe one of them had the right conditions for life to appear. The birth of life is not just rare, it's the result of an incredibly unlikely chain of events. If that's true, then we might be completely alone, not just as intelligent beings, but as the only living creatures in the entire universe. It's a chilling thought, based on cold, logical reasoning. And for those who dream of making contact with alien life, this might not even be the worst news. There's another challenge just as overwhelming: the rise of intelligence. It's an astonishingly complex and fascinating subject. While the rare Earth hypothesis has its fair share of critics, most of the objections focus on small details. No matter how harsh this idea may sound, it remains difficult to counter with a solid, well-supported alternative. And the facts make it even more unsettling. Humanity has investigated thousands of sightings of unidentified flying objects, sent astronauts to the moon, and deployed robotic explorers to Mars. We've listened for signals from space using powerful radio telescopes for many years, discovered thousands of planets beyond our solar system, and even launched probes that have left the sun's influence altogether. But despite all this effort, we find ourselves back at the same point: silence. For over 100 years, our television and radio broadcasts have traveled through space like a beacon. We've also sent intentional messages, bold yet hopeful attempts to contact extraterrestrial civilizations. The legendary search for extraterrestrial intelligence, or SETI, has enlisted thousands of volunteers worldwide to help analyze signals from the cosmos. But nothing. Absolute silence. Even when the massive Arecibo radio telescope in Puerto Rico tragically collapsed, there was no response from the heavens. No one came, no one noticed. Yet despite this unbroken silence, it would be wrong to declare that we are alone. The famous astronomer Carl Sagan often reminded us, absence of evidence is not evidence of absence. The possibility of life beyond Earth takes on a whole new meaning if the panspermia hypothesis is true. This theory suggests that life didn't just originate on Earth. It could have traveled across the cosmos, spreading to multiple planets. If so, then all those incredibly low probabilities scientists worry about may not matter at all. But there's a major flaw in how we search for life, especially intelligent life. We don't actually know what ingredients are required to create it. Even more puzzling, we don't fully understand what intelligence itself is, or what strange forms it might take. So why do we assume that only a certain type of intelligence, one that resembles our own, is possible? For all our efforts, we are ultimately searching for something familiar. We assume that alien life must be carbon-based like us. Yet scientists have long speculated about alternative forms of life, such as organisms based on silicon, and that's just the beginning. For instance, at pressures exceeding 460 gigapascals, compounds of nitrogen and hydrogen become even more chemically diverse than carbon-based molecules. If such chemistry leads to life, then nitrogen-hydrogen-based organisms could be even more varied and numerous than all known forms of life on Earth. And where would such creatures exist? Deep within the massive gas giants of our solar system, where nitrogen and hydrogen are abundant under extreme pressure. But that's another mystery entirely, another set of probabilities. For now, we continue searching for reflections of ourselves because, frankly, it's the only thing we know how to do. It's impossible to look for something when you have no idea what it is. The writer Stanislaw Lem spoke about this challenge at length. In reality, we aren't searching for just any kind of civilization. We are looking for one that mirrors our own. We impose human logic and scientific order onto the vast, unpredictable cosmos, hoping to find something recognizable. But what if we're looking in the wrong way? What if alien civilizations exist but are nothing like us? The fact that we haven't detected any signals doesn't necessarily mean no one is out there. There's something deeply unsettling about the silence of space. It's so complete, so overwhelming that it feels eternal. If the rare Earth hypothesis is correct, this great silence could mean that we are fundamentally alone in the universe. But should loneliness really be what we fear most? In the year 2023, a groundbreaking study published in Nature shook the scientific community. Data from the powerful James Webb Space Telescope revealed something that, according to current cosmological models, simply shouldn't exist. Astronomers had identified 6 enormous galaxies that appeared to have formed just 600 million years after the Big Bang. To put this into perspective, the universe is widely believed to be approximately 13 billion and 800 million years old. Yet these galaxies, which are unusually large, emerged far earlier than what scientists thought was possible. Based on everything we know, galaxies of this size should have taken billions of years to form, not a mere fraction of that time. In fact, calculations suggest that these galaxies should be at least 10 times smaller, or even 50 times smaller, than they actually are. The reason? There simply wasn't supposed to be enough ordinary matter, the building blocks of stars, planets, and life itself, available at that stage of the universe's evolution to create such massive structures so quickly. If these findings are verified, they could challenge one of the most fundamental assumptions in cosmology, the age of the universe. Some scientists now speculate that the cosmos might not be 13,800,000,000 years old, but instead an astonishing 26,700,000,000 years old, nearly twice as old as previously believed. This isn't just a minor scientific revision, it's a discovery that could rewrite our entire understanding of space and time. One of the study's authors, Erica Nelson, remarked that even if just one of these galaxies is real, it would push the limits of what we know about cosmology. So far, no existing scientific theories can fully explain this anomaly. However, some researchers have introduced a radical idea known as dark time, a concept suggesting that cosmic structures may have developed much faster than we ever imagined. If proven true, this would force scientists to rethink the fundamental principles of how the universe evolved. Despite our incomplete understanding of the universe's size and structure, we can assume that if it has boundaries, even vague or undefined ones, it should be theoretically possible to reach them. But what would that journey be like? Let's conduct a thought experiment. Imagine setting out in any direction through the vast expanse of space. Would your journey ever come to an end? If the universe does have an edge, what would it look like? Would you suddenly hit an invisible barrier? Would you pass through it into something else entirely? And if so, where would you end up? For centuries, humanity has pondered these very questions. Ancient civilizations fixated on the idea of a center and an edge to the universe. A famous 19th century engraving even illustrates how medieval people imagined the boundary of existence, beyond which lay the mysterious mechanisms controlling the cosmos. Now, if we look up at the night sky and focus on the massive red supergiant star Betelgeuse, we are not seeing it as it exists today. Instead, we're seeing it as it was 500 years ago because that is how long it takes for its light to reach us. In reality, Betelgeuse could have already exploded into a supernova, but we wouldn't know until the light from that explosion finally reaches Earth. Gravity works in a similar way to light when it comes to delays. We don't feel the sun's gravity in real time. Instead, the force we experience is coming from where the sun was 8 minutes and 20 seconds ago, because that's how long it takes for both sunlight and gravity to travel across space to Earth. This means that if the sun were to suddenly vanish without a trace, Earth wouldn't immediately be flung into the void. It would continue orbiting as if the sun was still there at its previous position for those 8 minutes and 20 seconds. Only after that time passes would our planet and the other planets in the solar system start drifting away in different directions. The same principle applies to galaxies. The Andromeda galaxy, the largest galaxy in our local group, is moving toward us at an astonishing speed of approximately 400,000 kilometers per hour. However, because we are seeing it as it was a long time ago, Andromeda is actually 900 light-years closer than it appears to be. To put that into perspective, the closest star to our Sun, Proxima Centauri, is 4 24 light-years away from us. Even with the fastest spacecraft we could possibly build today, it would take tens of thousands of years to reach that star. So, the fact that Andromeda is nearly 1,000 light-years closer than we think is an incredible realization. When we look into deep space, we can only see as far as the light that has had time to travel to us since the beginning of the universe. The farthest point from which light has reached us is a staggering 46 billion light-years away. This raises a big question. How can we see that far if the universe is only 13 8/10 billion years old? Shouldn't we only be able to see objects that are at most 13 8/10 billion light-years away? The answer lies in something called dark energy and the rapid expansion of the universe. It's not that the light from these distant objects has traveled to us in a straight line over all that time. Instead, space itself has stretched and expanded so much that we can now see much farther than the age of the universe would seem to allow. That's why we can observe objects 46 billion light-years away in every direction. This means that while the observable universe has a limit, the actual universe itself almost certainly extends far beyond what we can see. But where does it actually end? Is there a real physical boundary, or does space go on forever? To answer this question, let's conduct a thought experiment. What if we built a spacecraft, gathered a crew, and sent them on a mission to fly in a straight line as fast as possible to try and reach the edge of the universe? Astronomer David Kipping from Columbia University has explored this idea in great detail. He proposed that if we built a spaceship capable of accelerating indefinitely at a rate of 10 meters per second squared, we could get some interesting results. Why choose this specific rate of acceleration? Because at 10 meters per second squared, the passengers on board would feel a force equivalent to Earth's gravity. This means they wouldn't experience the weightlessness of space. Instead, they would feel as if they were simply standing on solid ground, just as they do on Earth. For reference, the acceleration due to gravity on Earth is actually 9 8/10 meters per second squared, but rounding it up to 10 makes calculations easier. In the first second, the ship would be moving at 10 meters per second. After 2 seconds, it would be traveling at 20 meters per second. By the end of the first hour, it would already be moving at an astonishing 35,280 meters per second, and it would keep accelerating. Within 2.5 hours, the ship would zoom past the moon. After 1 week, it would pass Saturn. At 11 days, it would be flying beyond Neptune, the farthest planet in our solar system. Of course, for this experiment, we are ignoring practical concerns like how much fuel the ship would need or the danger of colliding with cosmic debris. After traveling for 15 months, the spaceship would have covered 1 light year. At this point, however, strange things would begin to happen due to Einstein's special theory of relativity. At first, it seems like nothing is stopping the spaceship from accelerating indefinitely. But there is one major limitation. No object with mass can ever reach the speed of light. Take protons, for example. In the Large Hadron Collider, the most powerful particle accelerator on Earth, protons can be accelerated to nearly the speed of light, specifically 299,792,455 meters per second. At that point, you might think that adding just 3 more meters per second would push them past the speed of light. But no matter how much energy we pour in, they can only get closer and closer without ever actually reaching it. If not for this fundamental law, our spaceship would reach the speed of light in just 45 days. But reality doesn't work that way. Instead, as the ship gets closer to this limit, something bizarre happens. According to special relativity, the faster an object moves through space, the slower it experiences time. From an outside observer's point of view, the spaceship would appear to slow down as it approaches the speed of light. The people inside would seem to be moving in slow motion. However, for the crew on board, time would feel normal. They wouldn't notice any slowdown at all. In fact, from their perspective, it would appear as if time outside the spaceship was speeding up. At 15 months, when the spaceship reaches 87% of the speed of light, the effects of time dilation become significant. But even at speeds near light speed, time doesn't slow down evenly. It happens more drastically as the ship gets closer and closer to the ultimate limit. On the 15th of October in the year 1991, an incredible and mysterious particle from space reached Earth. Scientists were so astonished by its properties that they named it, "Oh my God." And when you hear what made it so special, you'll understand why. This tiny subatomic particle carried an unimaginable amount of energy, equivalent to a baseball traveling at a speed of approximately 94 kilometers per hour. Just think about that for a moment. A single particle, something so small that you'd never even notice it, held the same energy as a moving baseball. That alone is mind-blowing. But what truly shocked scientists was its speed. This particle wasn't just fast. It was moving at an absolutely astonishing rate. It was traveling at 99.9999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999% the speed of light. That means it was just a tiny fraction away from moving at light speed itself, something that no known object with mass should be able to do. To this day, scientists have no idea what could have possibly given this particle such an extreme boost in speed. What kind of force or event in the universe was capable of accelerating it to such a degree? No one knows. However, Recent observations using the telescope array project suggest that this particle may have originated from a region roughly 20 degrees wide in the direction of the Ursa Major constellation. That's all the information we have so far, but even that limited knowledge raises more questions than answers. Just imagining the possible source of such an incredible event is enough to send chills down your spine. One of the most bizarre aspects of this event is what happens to time when an object moves at nearly the speed of light. The effects of time dilation were so extreme for this particle that, from its own perspective, time was almost frozen. In fact, compared to a stationary observer, time for this particle slowed down by a factor of 300 billion. To put that into perspective, let's consider a journey across the cosmos. If humans wanted to travel from Earth to the Andromeda galaxy, which is approximately 2.5 million years away at the speed we currently understand, it would take us exactly that long, 2.5 million years. But for this particle, the same journey would have felt like it took less than 5 minutes. Now, if you think that's incredible, let's take this thought experiment one step further. What if a spaceship could travel at this speed? What would happen if it didn't stop and just kept moving forward? If a spaceship were to continue traveling far away from Earth, there's a specific point of no return in the universe, an invisible boundary, roughly 8.3 billion light-years away from us. If the spaceship crosses this threshold, it would be impossible for it to ever return, not because of a physical barrier, but because of the way space itself is expanding. At that distance, space is stretching away from Earth faster than the speed of light. This means that no matter how fast the spaceship accelerates, no matter how much energy is used to propel it back home, it would still be moving farther away rather than coming closer. This isn't a violation of physics, because the spaceship itself isn't exceeding the speed of light. It's the space around it that's expanding at that rate. To understand this, imagine a slinky toy. If you stretch a slinky, each individual coil moves only a tiny distance away from the next one. But if you look at the coils at opposite ends, they've moved a huge distance apart, even though each individual movement was small. This is what's happening with galaxies in the universe. They aren't physically moving faster than light, but the space between them is expanding at that rate. So if a spaceship crosses the 8.3 billion light-year mark, it's game over. No matter what the crew does, they would never be able to return home. It's a terrifying thought, being lost in space forever, with no hope of ever reconnecting with the place you came from. Now, let's take a step back and consider something even more mind-bending. Our visible universe, the part of the cosmos that we can currently see with our telescopes, is 46 billion light-years across in any given direction. However, because the universe is constantly expanding, that visible sphere is growing, and scientists estimate that it will eventually reach a size of about 61 billion light-years. But here's the catch. Just because something is visible doesn't mean it's reachable. Due to dark energy, a mysterious force that is accelerating the expansion of the universe, the cosmos has been split into different zones. The galaxies closest to us, within a distance of 15 billion light-years, are still technically reachable. If we could travel at the speed of light, we could, in theory, get to them. However, beyond that, things get much stranger. Galaxies that are between 15 and 46 billion light-years away are visible to us, but they are forever out of reach. No matter how fast we travel, we will never be able to reach them because they are receding from us at speeds faster than light. Even more astonishing, there are galaxies that are currently beyond the 46 billion light-year limit. These galaxies are completely invisible to us today, but in the far future, their light will finally reach us. That means that future generations of humans, if they are still around, will get to see galaxies that we can't even detect right now. But the most unsettling part, beyond the 61 billion light-year mark, there are galaxies that we will never see. Not today, not in 1 trillion years, not ever. They are beyond our cosmic horizon, permanently cut off from us. To illustrate just how drastic this expansion is, let's take a look at one of the most distant galaxies we've discovered so far, GNZ 11. This galaxy is 13.4 billion years old, meaning the light we see from it today was emitted just 400 million years after the Big Bang. However, because of the universe's expansion, GNZ 11 is actually 32 billion light-years away from us right now. We can still see this galaxy today, but soon its image will begin to fade. Eventually, it will disappear forever. The light GNZ11 is emitting at this very moment will never reach us. The universe's expansion is pushing it away too fast. And this isn't just happening to GNZ11. The reality is far more unsettling. Scientists estimate that more than 96.7% of the galaxies we can currently observe have already vanished beyond our reach. 98.6% of all galaxies that will ever be visible to us are already lost in the expanding universe. In total, we were theoretically supposed to see 4,700,000,000,000,000 galaxies in the history of our observations. Out of those, 4,634,000,000,000 galaxies have already disappeared. That leaves only 66 billion galaxies still within reach, and it gets worse. Every second, roughly 60,000 stars disappear from our field of view forever. That's tens of millions of stars vanishing every day, stars that once existed within the observable universe. Imagine looking up at the night sky and seeing stars that are already gone. They might have burned out millions or even billions of years ago, yet their light is still traveling through space, reaching our eyes long after they ceased to exist. Now take that idea and magnify it to a cosmic scale. There are entire galaxies that at this very moment are vanishing from our reach, not because they are disappearing in the literal sense, but because the universe is expanding so rapidly that any new light they produce will never reach us again. This means that for all practical purposes, these distant galaxies have ceased to exist from our perspective. They still exist somewhere out there, but they are beyond our grasp. No matter what we do, we can never interact with them again. We cannot send signals, we cannot observe new changes, and they can no longer affect us in any way. In a sense, they have been erased from our version of reality, locked away in a part of the universe that we will never see again. If the force causing the universe to expand continues to grow stronger, then eventually, even the galaxies closest to us will drift away into the void. Over time, each galaxy will be left alone in total isolation. Stars will exhaust their fuel and burn out, leaving behind cold, lifeless remnants. The particles that make up everything we know, planets, people, even atoms themselves, will eventually decay. Even the mighty black holes, which seem almost eternal, will slowly evaporate due to a phenomenon known as Hawking radiation. This process takes an incomprehensibly long time, but in the end, even black holes will vanish. What will remain? Just empty space, stretching out forever, with nothing in it but a mysterious force known as dark energy. Dark energy is one of the strangest concepts in modern physics. Unlike gravity, which pulls things together, dark energy does the opposite. It pushes space itself apart. What makes it even stranger is that as space expands and becomes emptier, dark energy doesn't weaken. Instead, it stays constant or even becomes stronger. This creates a feedback loop. The universe expands, which leads to more empty space, which then allows dark energy to accelerate the expansion even more. This cycle continues indefinitely, meaning the universe will keep growing at an ever-increasing rate. In time, events happening in one part of the universe will no longer have any effect on what happens elsewhere. Everything will be separated by such vast distances that even light won't be able to bridge the gap. Eventually, the universe will be nothing but an enormous, endless void, where nothing happens and nothing ever changes. This is the ultimate fate of the cosmos, an empty, silent expanse, expanding forever with no end. Now let's imagine an extraordinary scenario. Suppose we built a spaceship capable of traveling at nearly the speed of light. If the crew on board set off on a journey and their ship's clock reached its 200th year, an almost unimaginable amount of time would have passed in the rest of the universe. To be precise, 10 to the power of 41 years, meaning a 1 followed by 41 zeros. By that time, the universe would have changed drastically. Space would have stretched to such an extreme extent that the spaceship might be the only structure left within its observable region. No stars, no planets, no galaxies, just an endless pitch-black void. The crew would be sailing through a universe that had already faded into emptiness. So could they ever reach the edge of the universe? The answer is no. The expansion of space would outpace even their near-light-speed travel. No matter how fast they moved, they would never find an actual boundary, because the universe isn't something that has a defined outer edge. This brings us to a fascinating and somewhat mind-boggling idea. What if the universe has no edge, but it is still not infinite? For centuries, people have wondered whether the universe stretches on forever, or if it has some kind of limit. A famous philosophical argument proposed over 2,000 years ago by the Greek thinker Archytas asked a simple yet profound question. If you could stand at the edge of the universe and throw a spear, what would happen? Would the spear hit a wall and bounce back? If so, what is on the other side of that wall? And if it passes through, then the universe must extend even further. If we follow this logic, there must always be something beyond, no matter how far we go, meaning the universe must be infinite. This paradox puzzled philosophers and scientists for centuries. But what if the answer isn't as straightforward as finite or infinite? What if the universe has edges but still goes on forever in a different sense? To understand this, we need to look at a surprising discovery made in the 19th century by one of history's greatest mathematicians, Carl Friedrich Gauss. For most of history, people believed that the angles of a triangle always add up to 180 degrees. This is true on a flat surface, but Gauss suspected that space itself might not be completely flat. Imagine living on a massive sphere, like the surface of a planet. If you draw a tiny triangle on the ground, it will behave just like a regular triangle on paper. Its angles will add up to 180 degrees. But if you draw a gigantic triangle, one that covers a significant portion of the planet, you'll notice something strange. The sum of its angles will be greater than 180 degrees. This happens because the surface of the sphere is curved. Gauss wondered whether the same principle could apply to the universe itself. If space was curved in some way, then the geometry we take for granted might not hold true on a large scale. To test this idea, Gauss secretly measured the angles of a huge triangle formed by 3 mountain peaks in what is now Germany. His goal was to see if their sum deviated from 180 degrees. Unfortunately, the difference was too small to be certain, so he never announced his findings. Decades later, Albert Einstein's theory of general relativity confirmed that space is indeed curved by gravity. More precise measurements have since shown that near Earth, the angles of a triangle can actually add up to slightly more than 180 degrees, about 180.2 degrees. So what does this tell us about the shape of the universe? If space is curved on a large scale, it could mean that the universe is finite but has no edges. One way to picture this is to imagine the surface of a balloon. A 2-dimensional being living on the surface of the balloon would never encounter an edge, but their world would still be finite. If they kept walking in one direction, they would eventually return to where they started. If our 3-dimensional universe works the same way, then it might not have an edge, but it also wouldn't go on infinitely in a straight line. Instead, it could curve back on itself in a way that is difficult for us to visualize. So where does this leave us? The universe is expanding at an ever-accelerating rate, driven by the mysterious force of dark energy. The galaxies we see today will one day drift beyond our reach, and eventually, all that will remain is an empty void. We often imagine the universe as an endless expanse stretching in all directions, but what if that's not entirely true? Scientists have long been trying to determine the actual shape of the universe, not just how it appears to us from within. A crucial clue to this mystery lies in something called curvature, a mathematical property that could reveal whether the universe is truly infinite or if, in some way, it is enclosed within itself. At first, it might seem impossible to grasp how the universe can be both boundless and closed at the same time. But let's consider an analogy that makes this concept easier to understand: the surface of the Earth. If you start walking in any direction, you won't encounter an edge. Instead, if you keep going long enough, you will eventually return to the place where you started. This happens because Earth's surface, while appearing limitless when you stand on it, is actually curved into a closed shape. Now imagine a similar idea, but instead of a 2-dimensional surface like Earth's, apply it to 3-dimensional space. Could the entire universe be curved in such a way that if you traveled in a straight line long enough, you'd eventually return to your starting point? It's a mind-bending concept, and even the greatest physicists struggle to visualize it. Since our brains aren't wired to picture such a reality, we turn to mathematics to help us explore the possibilities. Over the years, scientists have conducted extensive research on this topic and have identified not just one but 18 different possible shapes, or topologies, for the universe. These possible structures fall into 2 broad categories: orientable and non-orientable universes. To understand the difference between these categories, let's look at a fascinating two-dimensional shape known as the Mobius strip. You can create a Mobius strip by taking a long strip of paper, giving it a single twist, and then connecting the two ends. What makes this shape so special? If you place a dot on the strip and start tracing a continuous path along its surface, you will eventually return to your starting point. But flipped. In other words, the orientation is reversed. If you had written text on one side of the strip, when you return to your starting position, the text would appear mirrored. In geometry, such surfaces are called non-orientable, meaning they contain paths that flip the orientation of objects traveling through them. In contrast, shapes like a sphere or a donut-shaped torus are orientable, meaning they don't have this strange flipping property. Now, imagine that our entire universe is structured like a Mobius strip, but in 3 dimensions. If this were the case, something truly bizarre would happen. If you traveled far enough in a straight line, you would eventually return home, but everything would be mirrored. This might sound like something out of a science fiction novel, but mathematically, it's a real possibility. However, most cosmologists doubt that we live in such a universe. One reason is that if the universe were non-orientable, there would likely be regions where normal matter and its opposite counterpart, antimatter, interact. This interaction would produce detectable energy emissions, but so far, no such emissions have been observed. That doesn't entirely rule out the idea, though. It's still possible that such regions exist far beyond the part of the universe we can observe. One way scientists test these theories is by measuring the curvature of space over vast distances. Near massive objects like stars and black holes, space is definitely curved, but when measured on a much larger scale, the data suggests that the universe is astonishingly flat, at least within the limits of our observations. If the universe is truly flat, this has profound implications. It suggests that the universe could be infinite because a truly infinite universe would naturally appear flat at large scales, and this leads to some mind-blowing consequences. Theoretical physicist Max Tegmark explored this idea in his book, Our Mathematical Universe. He calculated that the number of possible ways particles can arrange themselves within the observable universe is roughly 10 to the power of 10 to the power of 118. That is an unimaginably huge number, so vast that our minds can't fully grasp it. But if the universe is truly infinite, then something astonishing must be true. Somewhere out there, far beyond the region we can observe, there must be another Earth that is exactly like ours. Imagine drawing a straight line from Earth in any direction. If you traveled a distance equal to 10 to the power of 10 to the power of 118 times the diameter of our observable universe, you would theoretically arrive at an identical copy of Earth, with an identical version of you, thinking the exact same thoughts at this very moment. This idea might seem even stranger than the concept of a mirrored universe. But unlike the Mobius strip scenario, where a flipped copy of reality would exist, an infinite universe implies that every possible arrangement of particles must exist somewhere, no matter how unlikely. Now let's take this thought experiment even further. What happens if we consider not just infinite space but also infinite time? The answer is simple yet profound. In an infinite universe with infinite time, everything that is physically possible must eventually happen. Even if we imagine a vast, empty region of space where no particles exist, modern physics tells us that this space is never truly empty. Quantum fields, the fundamental fields that govern the universe, are constantly fluctuating. These fluctuations, known as quantum fluctuations, are an unavoidable consequence of Heisenberg's uncertainty principle. Over a long enough period, these fluctuations could lead to highly unusual events, such as the spontaneous formation of complex structures or even an entire new universe appearing out of nothing. While this might sound like pure science fiction, it's actually a natural prediction of modern quantum physics. Imagine a universe so vast and endless that even the most impossible events are not just possible but guaranteed to happen, given enough time. You might be thinking, come on, are you really saying that if we wait long enough, something as ridiculous as a grand piano appearing out of nowhere in the middle of an empty universe could actually happen? As crazy as it sounds, this idea has been seriously examined by some of the greatest minds in modern physics, including Anthony Aguirre, Sean M. Carroll, and Matthew C. Johnson. They even ran the numbers and came to a shocking conclusion. If you were to wait for a period of time so long that it makes the current age of the universe seem like the blink of an eye, something like a trillion times longer, you would eventually witness that piano materializing right in front of you. As unbelievable as this may seem, it all follows directly from the fundamental laws of physics as we currently understand them. The more unlikely an event is, the longer you have to wait for it to occur. But in a universe with infinite space, infinite time, or both, even the most improbable events will happen, not just once, but an infinite number of times. That's the unsettling reality of infinity. If time truly stretches on forever, then our own universe will inevitably repeat itself, down to the finest detail. That means you will watch this exact video again, not just once, but an infinite number of times. While some might find this concept thrilling, others might find it downright terrifying. It raises the unsettling question, is the universe truly infinite, or is there some kind of boundary to all of this? Now, some scientists argue that the universe could still be finite, just incredibly vast and curved in ways we can't yet measure. The tools we currently use tell us that the universe appears to be flat with an accuracy of 99.75%. However, if it isn't perfectly flat, then it must be at least 400 times larger than the observable universe, spanning a mind-boggling 37,200,000,000,000 light-years across. But here's the twist. Even if the universe is closed, that doesn't necessarily mean it's curved in a way we expect. Consider the surface of a cylinder. It's geometrically flat because parallel lines remain parallel, yet it can extend indefinitely. The universe might work in a similar way. There's even a possibility that our universe is shaped like a four-dimensional torus, a shape where space appears perfectly flat, yet if you travel far enough in a straight line, you would eventually loop back to your starting point. In contrast, a four-dimensional sphere would behave differently. Angles in a triangle would add up to more than 180 degrees, and parallel lines would eventually meet. The true shape of our universe is something we, as three-dimensional beings, might never fully grasp. To truly perceive it, one would need to exist in 4 dimensions. This leads us to an idea that might surprise many. The edge of the universe isn't some far-off boundary. It is quite literally all around us. To understand this, imagine a world that exists in only 2 dimensions, a flat plane that might stretch infinitely or loop back on itself. Now imagine that within this 2-dimensional world, there exist 2-dimensional beings, completely unaware of the 3rd dimension. To them, their world seems complete, but from our 3-dimensional perspective, we could see every atom of their existence as if it were laid bare before us. The edge of their universe would be obvious to us, but to them, it would remain invisible. Now, apply the same logic to our 3-dimensional universe. The 4th dimension is not some distant realm. It is everywhere, surrounding every single atom of our existence. We are completely immersed in it, yet we have almost no way of interacting with it. It is, quite literally, the true boundary of our universe, always present but forever just beyond our reach. And beyond that remains an enigma, a mystery wrapped in the vast emptiness of existence itself. Imagine a place where nothing exists for an unfathomable distance, a place so utterly empty that it feels as though time itself has come to a complete stop. There is no light, no stars, no galaxies, just an endless abyss of absolute darkness stretching for what seems like forever. We live on a planet that orbits the Sun, which in turn is part of the Milky Way galaxy. The Milky Way does not exist in isolation. It is part of a collection of approximately 50 galaxies that make up the local group. This local group itself is just a small portion of a much larger cluster known as the Virgo supercluster. But it doesn't end there. The Virgo supercluster, along with many other superclusters, is a fragment of something even more immense, a gigantic structure called the Laniakea supercluster. Unlike planets or moons that orbit a central body, these massive galactic clusters do not revolve around a single point. Instead, they move under the gravitational pull of a mysterious and powerful anomaly known as the Great Attractor, which lies hidden at the center of our local cosmic neighborhood. Yet, our focus today is not on this gravitational giant. Instead, we will explore something far more eerie, the vast, desolate nothingness that lies in front of it. This empty region is called the dipole repeller, a place where the pull of gravity is so weak that matter seems to avoid it. These barren areas in space are known as voids, and they are some of the largest structures in the universe, making up most of its volume. If we could see the cosmos from a great distance, it would resemble a massive web. Galaxies connected by luminous threads, separated by vast, pitch-black voids. And among these voids, there is one that stands out as one of the most puzzling and terrifying of all, the booties void. When we look up at the night sky, it appears as though the stars are evenly scattered across the heavens. But this is an illusion. Stars are actually clumped together in galaxies, and those galaxies form gravitational clusters. The gaps between these clusters may seem vast, but they are insignificant when compared to the scale of cosmic voids. The booties void is one of the largest known voids in the entire universe. It is located roughly 700 million light-years away from Earth in the direction of the Booties constellation, which is how it got its name. This colossal region was first discovered in the year 1981 by astronomer Robert Kirshner and his research team. From the moment of its discovery, scientists have been baffled by its immense size and unexplained emptiness. How could such a massive region of the universe be so devoid of matter? What could have caused this vast desert in space? To grasp just how enormous the Bootes void is, consider this. Its diameter is estimated to be approximately 330 million light-years. To put that into perspective, this single void spans 27% of the total diameter of the observable universe. For comparison, the Milky Way galaxy, which is already mind-bogglingly vast, is only about 100,000 light-years across. That means you could fit over 3,000 Milky Ways side by side within this void. When scientists first began investigating the Booties void, they expected to find thousands of galaxies scattered throughout the region. However, their findings shocked them. Initially, they could only detect 8 galaxies within this immense space. That number has since increased, but even now, only 60 galaxies have been identified. To understand how unusual this is, consider the Andromeda galaxy, our closest galactic neighbor. It is located about 2.5 million light-years away from us. If galaxies were evenly distributed throughout the universe, the Bootes void should contain at least 2,000 galaxies, but instead, it contains only a tiny fraction of that number. Astronomer Greg Aldering from the University of Minnesota explained the scale of this mystery in a striking way. If our Milky Way galaxy were located at the center of the Bootes void, we would not have known that other galaxies even existed until the 1960s. The vast emptiness would have prevented us from seeing them with telescopes before that time. The sheer emptiness of the Bootes void has led many scientists to call it one of the strangest places in the universe. The density of galaxies in this region is so low that it almost defies rational explanation. To understand why this is so bizarre, let's compare it to our own cosmic neighborhood. Within just 3 million light-years, our Milky Way galaxy has over 24 nearby galaxies. In contrast, the Bootes void has an average galaxy separation of over 10 million light-years, 4 times the distance between the Milky Way and Andromeda. If the universe were uniformly distributed, this void should contain at least 10,000 galaxies. The fact that it does not raises many unsettling questions. How did such a vast empty region come into existence? Is it simply a natural feature of the universe, or could something else be at play? Scientists have attempted to calculate the true volume of the Bootes void. Since traditional units struggle to express such massive distances, they use a unit called the parsec, which is equal to 3 light-years. Using this measurement, they estimate that the total volume of the Bootes void is approximately 236,000 cubic megaparsecs. To put it simply, this void is so large that if it were filled with galaxies at the usual density, it could contain thousands of times more matter than it currently does. So what exactly is inside the Bootes void? The paradoxical answer is almost nothing. It is a cosmic desert, almost entirely devoid of matter. Unlike the rich environments of other galaxies, where stars, planets, gas clouds, and cosmic dust swirl together in a dance of creation and destruction, the Bootes void is eerily silent. Even tiny particles such as photons, the fundamental particles of light, are sparse in this dark expanse. This is why some scientists refer to the Bootes void as the ultimate cosmic desert. The Bootes void is so dark and desolate that some researchers have described it as a place where time itself appears to stop. In most galaxies, interactions between stars, planets, and cosmic forces drive the passage of time, creating change and motion. But in the booties void, nothing seems to happen. There is no significant activity, no major forces at play, just a profound stillness that stretches across millions of light years. To put it into perspective, dust and dirt, common nuisances on Earth, are almost non-existent here. But even more astonishing is the fact that particles themselves, the very building blocks of the universe, barely interact. If they do, it could take thousands upon thousands of years for such an event to occur. This extreme emptiness has a bizarre effect. When streams of neutrinos, nearly massless particles, enter one side of the void, they emerge from the other side completely unchanged. The same applies to photons, the particles of light. Matter, which is much heavier, doesn't share this fate. It gets slowly pulled toward the outer edges of the void, where a few lonely galaxies still remain. Because of this unique property, where light and energy remain unaltered, the booties void might one day serve as the ultimate time capsule. Imagine firing a beam of photons across this vast chasm, only for it to be rediscovered hundreds of millions of years later when it reaches the other side, unchanged, a relic of a long-lost past. But beyond being a cosmic archive, this place could also serve a more futuristic purpose. With no intergalactic dust to slow them down, advanced spacecraft could use this vacuum as the ultimate testing ground, perhaps one day pushing the limits of speed to 99.99% of the speed of light. Yet the biggest mystery surrounding the booties void isn't just what it could be used for, it's how it even came to exist in the first place. Compared to the rest of the universe, it is an anomaly unlike anything we've ever seen. Some scientists believe it was formed when several smaller voids combined, much like how tiny soap bubbles merge into a single large bubble. In support of this idea, astronomer Greg Aldering observed that the galaxies inside the void seem to be arranged in strange tube-like structures. He suggested that these galaxies might be remnants of the boundaries where smaller voids once met before collapsing into a single vast emptiness. If the universe lasts long enough, even these galaxies might one day be pulled out by the relentless force of gravity, leaving behind an even purer, darker nothingness. But what if the explanation is far more unbelievable? Some have speculated that the booties void was not formed naturally at all, that it may be the result of an ancient, hyper-advanced civilization. According to this theory, a Kardashev Type 3 civilization, one capable of harnessing the energy of entire galaxies, might have methodically expanded across this region. As it advanced, it could have dimmed or even completely hidden each star it encountered by surrounding it with massive Dyson spheres, structures designed to capture all of a star's energy output. This would explain the near-perfect spherical shape of the void, as well as why it is so completely devoid of visible matter. Given that the void is about 700 million light-years from Earth, and that intelligent life in the universe could have emerged as early as 4 billion years ago, such a civilization would have had more than enough time to accomplish this mind-boggling feat of engineering. Of course, this is purely speculation, but considering how strange the booties void is, it's a theory worth pondering. One thing is certain. Its discovery has forced astronomers to rethink everything they thought they knew about the structure of the universe. Galaxy formation is now seen in a new light, as we realize just how unevenly matter is distributed throughout the cosmos. Have you ever wondered if there could be another version of yourself living a completely different life in a world that exists alongside ours? Could it be possible that what we consider our reality is just one among many? Some scientists and philosophers suggest that our perception of life as a continuous journey through time and space may be nothing more than an illusion. Instead of being confined to a single path, our existence could be an ever-branching series of events, splitting off moment by moment into countless possibilities. If this idea holds true, then multiple versions of you exist simultaneously, each experiencing a different reality. In a way, this would mean you are, in essence, immortal, because somewhere in some other universe, another version of you always exists. In this exploration, we will dive into fascinating discoveries that might hint at the existence of a multiverse. We'll discuss an extraordinary form of radiation that fills the cosmos, known as the cosmic microwave background radiation, CMB, and why it has captivated scientists for decades. We'll look at the evidence that might suggest parallel universes are real, Consider whether there's a possibility for another life beyond this one, and explain how the famous thought experiment Schrödinger's cat and Albert Einstein relate to all of this. Along the way, we will also dispel some popular misconceptions and uncover the first significant clues that might point to the reality of a multiverse. Our story begins in the year 1948, when a brilliant physicist named George Gamow, who was born in Russia but later moved to the United States, made a groundbreaking prediction. He theorized that if the universe had originated from an unimaginably powerful explosion known as the Big Bang, then some residual radiation from that event should still be present. According to his calculations, this radiation should have a temperature of approximately 50 degrees Kelvin, which is equivalent to a frigid negative 2,167 degrees Celsius. However, Gamow's estimate was off by more than a factor of 10. When this radiation was finally detected, its actual temperature turned out to be only 2.7 degrees Kelvin, just slightly above absolute zero. The discovery itself was a complete accident. In the year 1965, two American scientists, Arno Penzias and Robert Wilson, were working at Bell Laboratories, using a radio antenna originally built in the early 1960s for one of the first communication satellite systems. The satellites themselves were no longer in use, and they had been safely destroyed as they re-entered Earth's atmosphere. Penzias and Wilson were attempting to study the emission of neutral hydrogen, an abundant element in the universe, but their efforts were constantly disrupted by an unexplained background noise. No matter what they did, the mysterious microwave interference remained. At first, they thought the problem might be caused by military tests or some form of radio interference coming from New York City. When that explanation didn't hold up, they even suspected that pigeon droppings inside the antenna might be causing the strange signal. However, after thoroughly cleaning the equipment, the noise persisted. It was only later that they realized they had stumbled upon something incredible, the very radiation that scientists had been searching for, the cosmic microwave background radiation. For their accidental yet monumental discovery, Penzias and Wilson were awarded the Nobel Prize in the year 1978. What made this discovery so extraordinary was that it confirmed a major part of the Big Bang theory. Scientists soon realized that this radiation wasn't just coming from one direction, it was everywhere. No matter where in the universe you looked, the radiation had the same temperature. It was like an invisible ocean, surrounding and permeating everything. While the CMB appeared to be remarkably uniform, there were tiny fluctuations in temperature, as predicted by theoretical models. On average, these variations were about 18 microkelvin, which is an extremely small difference. If you were to map out the temperature of this radiation across the sky, it would resemble a patchwork quilt or gentle ripples on a pond's surface. Fast forward to the year 2004, when a NASA satellite named WMAP was conducting detailed studies of the cosmic microwave background radiation. This probe was designed to map out the tiny fluctuations in the radiation's temperature that had been present since the universe was just 380,000 years old. However, when scientists analyzed the data, they found something truly bizarre, a cold spot in the radiation that was much larger and much colder than expected. So why is this cold spot so mysterious? Its temperature is significantly lower than the surrounding radiation. While the average temperature fluctuation in the CMB is about 18 microkelvin, this particular region was measured at around 70 microkelvin, and at its center, it could drop as low as 50 microkelvin. Imagine an ocean where the average wave height is just a few centimeters, and then suddenly you encounter a massive, towering wave that stretches several meters high. That's how unusual this cold spot is compared to the rest of the universe. Its sheer size is mind-boggling. The cold spot is estimated to be nearly 2 billion light-years across. To put that into perspective, our own Milky Way galaxy is just 100,000 light-years wide. This means that the cold spot could fit nearly 20,000 galaxies the size of the Milky Way inside it. If that comparison doesn't quite capture its scale, consider this. The landmass of the United States is roughly equivalent to 8,000 copies of New York City. Now imagine a cosmic void so vast that it dwarfs all of that, by an unimaginable factor. Scientists believe that this cold spot corresponds to an enormous void in space, an area where there is an unusually low number of galaxies, stars, and other cosmic structures. This region, located in the constellation Eridanus, has been given the name the Eridanus supervoid. If you were somehow able to travel to the center of this void, you would find yourself surrounded by complete and total darkness. No stars, no galaxies, just an endless, freezing expanse of nothingness. It would be an environment unlike anything we have ever known, devoid of light, gravity, and any sense of orientation. It might be one of the darkest, most mysterious places in the entire universe. But how did this void come to be? And could it hold secrets about the nature of our reality? Some researchers have proposed that this supervoid might be more than just an empty region of space. One fascinating theory suggests that the eridanus supervoid could be the after effect of a collision between our universe and another universe in the multiverse. In other words, this cold spot might be a cosmic scar, a remnant of an interaction between two parallel realities. If this hypothesis is correct, then the cold spot could be one of the first tangible pieces of evidence that parallel universes exist. While this idea remains speculative, it is being seriously considered by some of the world's leading physicists. For decades, scientists have studied the vast, empty spaces in our universe known as voids. These regions are enormous cosmic gaps where galaxies and galaxy clusters are scarce, making them some of the least dense areas in the known cosmos. Compared to the more populated regions of space, voids have about 10 times less matter. The first discovery of these voids happened in 1978, when astronomers Stephen Gregory and Laird Thompson, working at Kitt Peak National Observatory in Arizona, identified these peculiar gaps in the cosmic web. They vary significantly in size, ranging from 30 million to 300 million light-years across. However, one particular void, known as the eridanus supervoid, defies explanation. It is unimaginably vast, with a span of nearly 2 billion light-years, a size that far exceeds any previously discovered voids. This discovery raises troubling questions. If the universe expanded uniformly after the Big Bang, as most scientists believe, how could such a gigantic empty space form? The standard Big Bang theory can account for regular voids, but something as massive and unusually cold as the eridanus supervoid should not exist. It is an outright anomaly, one that has left scientists puzzled and searching for answers. Since its discovery, scientists have proposed several fascinating explanations for the existence of this cosmic anomaly. These ideas range from purely scientific to the truly mind-bending. Let's explore them in detail. One of the earliest theories suggested that the eridanus supervoid could actually be a supermassive black hole, an enormous gravitational monster that devours everything in its vicinity, leaving behind a vast, empty region. Some speculated that this cosmic behemoth could continue expanding over time, swallowing planets, stars, and even our own galaxy. But before you start worrying about Earth being consumed, there's good news. First, the void is 3 billion light-years away, meaning it would take an incredibly long time for any hypothetical black hole there to have an impact on us. Second, calculations show that a black hole large enough to create such a void would need to be absurdly massive, far beyond anything science currently understands. To put it into perspective, even a black hole with a mass of 100 million suns would be significantly smaller than our sun in terms of its physical size. That means, despite its immense gravitational pull, it could not create such a gigantic void simply by consuming matter. Another possibility involves dark matter, the mysterious, invisible substance that makes up most of the universe's mass. Unlike normal matter, dark matter does not interact with electromagnetic forces, meaning we cannot see it, but we can detect its presence through gravitational effects. According to widely accepted cosmological models, every part of the universe, including voids, should contain at least some dark matter. However, researchers examining the eridanus supervoid noticed something strange. There was no sign of dark matter at all. If this void had a typical amount of dark matter, its radiation signature would be different, and its gravitational pull would be stronger. This absence leads to an unsettling possibility. What if dark matter doesn't exist at all? If the eridanus supervoid truly lacks dark matter, it could mean that the entire Big Bang model, the very foundation of modern cosmology, is incomplete or even incorrect. Without dark matter, many of the equations used to explain the universe simply wouldn't work. But before we throw out decades of scientific research, it's important to remember that there is a lot of evidence supporting the existence of dark matter. The mystery remains. Why is this particular region seemingly devoid of it? If neither black holes nor missing dark matter explain the eridanus supervoid, then what could? Some scientists believe the answer lies beyond our universe itself. According to an extraordinary hypothesis, this void could be the first physical proof of the multiverse, the idea that our universe is just one of many universes coexisting in a vast cosmic ocean. But how could we possibly see evidence of another universe? The answer might lie in what's called the cosmic microwave background, CMB radiation. This is the faint, ancient radiation left over from the Big Bang, and it acts like a fingerprint of the early universe. Strangely, when astronomers looked at the CMB map, they found a cold spot precisely where the eridanus supervoid is located. This suggests that something incredibly unusual happened in this region billions of years ago, something that standard physics cannot fully explain. Could this be the scar of a collision between universes? Some physicists propose that long ago, our universe may have collided with another universe, leaving behind an imprint on the cosmic microwave background. In other words, the eridanus supervoid might be the site of a cosmic crash, a place where two bubble universes made contact. This idea is supported by the work of physicists Anthony Aguirre, Matt Johnson, and Matt Kleben, who showed that if our universe had ever collided with another, it would leave behind a distinct circular mark in the CMB. That's exactly what we see in the eridanus supervoid. If true, this would be one of the greatest discoveries in history. It would prove that our universe is not alone, and that there may be countless other universes, possibly even with their own stars, planets, and civilizations. To understand why the multiverse theory is taken seriously, we need to take a brief detour into quantum mechanics, the branch of physics that deals with subatomic particles. One of the most famous experiments in quantum mechanics is the double-slit experiment. In this experiment, when scientists shine light or fire tiny particles through two slits, they see an interference pattern on the screen behind it, as if the particles behave like waves. But when they try to observe the particles, they behave like solid objects instead. This bizarre behavior suggests that particles exist in multiple states at once, a principle known as superposition. Some scientists believe this supports the many worlds interpretation, which suggests that every time a quantum event happens, the universe splits into multiple realities. If this interpretation is correct, then the multiverse is real, and the eridanus supervoid could be the first physical evidence of another universe colliding with ours. Imagine you are standing by the edge of a calm lake, holding a small stone in your hand. You toss the stone into the water and watch as ripples spread out in perfect circles. Now, imagine throwing two stones at the same time, just a little distance apart. What happens? The ripples from each stone collide and form a pattern, a mix of peaks and dips where the waves either add up or cancel each other out. This is called an interference pattern, and it is something that naturally happens with waves. But what if you were told that tiny particles, the building blocks of everything around us, can behave like these waves? And even stranger, what if simply watching them could change their behavior? This is one of the biggest mysteries in physics, and it all starts with a simple experiment. Scientists wanted to see how waves and particles behave when they pass through a narrow opening, or slit. They set up a barrier with a thin slit cut into it, and behind this barrier, they placed a screen that would show where the waves or particles landed. When they sent waves, like water waves or even light waves, through the slit, the waves spread out and hit the screen, forming a bright band directly in line with the slit. No surprises there. Then they did the same experiment with tiny particles, like electrons, which are part of atoms. When electrons were sent through the slit one at a time, they acted exactly as expected. They hit the screen in a straight line, just like tiny bullets being fired from a gun. Everything made sense so far. Next, scientists added a second slit next to the first one and repeated the experiment. Here's where things took a bizarre turn. When waves passed through both slits, something interesting happened. Instead of forming two bright bands on the screen, like you might expect, the waves interfered with each other, creating multiple bright and dark bands. This pattern showed where the waves had combined, getting stronger, or cancelled each other out. But what about particles? If electrons were like tiny bullets, You'd expect them to pass through either one slit or the other and form two straight lines on the screen, right? That's not what happened. Instead, the electrons somehow created the same interference pattern as waves. Instead of two lines, they made many bright and dark bands. But how could individual particles, shot one at a time, behave like waves? At first, scientists thought maybe the electrons were bumping into each other, causing them to scatter and create the interference pattern. To test this, they slowed things down and shot one electron at a time. This meant that each electron traveled alone, with no chance of hitting another electron. But even when fired one by one, the electrons still created the interference pattern. This meant that somehow, a single electron was behaving like a wave, spreading out and interfering with itself as if it had passed through both slits at the same time. To solve the puzzle, scientists decided to watch the electrons and see which slit each one passed through. They placed a measuring device near the slits to track the electrons. And then something even stranger happened. As soon as they observed the electrons, the interference pattern disappeared. Instead of behaving like waves, the electrons started behaving like regular particles, forming two straight lines on the screen, just like tiny bullets. This meant that the mere act of observing the electrons changed their behavior. But how? Was the electron aware that it was being watched? Did the universe behave differently depending on whether or not someone was looking? This bizarre discovery led to some of the most mind-blowing theories in science, theories that could change everything. One of the most famous explanations comes from physicists Werner Heisenberg and Niels Bohr in the early 20th century. Their idea, known as the Copenhagen interpretation, says that before we observe a particle, it doesn't exist in a single definite state. Instead, it exists in all possible states at the same time, as a kind of blur of possibilities. When we observe the particle, we force it to choose one state. In other words, an electron is not really in one place or the other until we look at it. This idea troubled many scientists, including Albert Einstein, who famously said, "God does not play dice." He refused to believe that the universe was ruled by randomness and probability. Another scientist, Erwin Schrödinger, created a famous thought experiment to challenge this idea. Imagine you have a cat inside a box. In the box, there is a radioactive atom that has a 50% chance of decaying, breaking down within 1 hour. If it decays, it triggers a mechanism that releases poison gas, killing the cat. If it doesn't decay, the cat remains alive. But according to quantum mechanics, until you open the box and check, the atom is in a superposition. It is both decayed and not decayed at the same time. And because the cat's life depends on this, the cat must also be in a superposition, both alive and dead at the same time. Only when you open the box does reality decide whether the cat is alive or dead. This sounds absurd, and Schrödinger actually meant it as a criticism of the Copenhagen interpretation. He was saying, surely this can't be how reality works. But if that's not how reality works, then what's really going on? Another possible explanation, known as the many worlds interpretation, suggests that all possibilities actually happen, but in separate universes. In this theory, every time you make a decision, the universe splits into multiple parallel realities. If you flip a coin, there is one universe where it lands on heads and another where it lands on tails. Applying this to the double slit experiment, when an electron passes through the slits, it goes through one slit in one universe and the other slit in a different universe. We just happen to see only one outcome because we are inside just one of these countless branching realities. This idea is straight out of science fiction, but it's taken seriously by some of the world's top physicists. Now let's go one step further. If observation can change reality, what if reality itself is not real? Some scientists believe that our entire universe could be a simulation, like a giant computer program. In a video game, objects only fully render when a player looks at them. What if electrons behave the way they do because we are inside a simulated reality, and things only exist when they are observed? It sounds crazy, but there are serious arguments for this theory. If true, it would mean our universe is not the base reality, but just one of many simulated worlds. Have you ever wondered just how much computers have advanced since the early days? Let's take a guess. Have their capabilities increased hundreds of times, maybe thousands? Well, the real answer is mind-blowing. Since the 1940s, Computers have become hundreds of trillions of times more powerful, and that's not even the end of it. Experts predict that in the next few decades, their power could grow millions of times more. Now, why does this matter? Because this kind of computing power could allow us to create virtual worlds so advanced that the characters inside them wouldn't just follow pre-programmed instructions. They could be as complex as us, with thoughts, emotions, and even consciousness. But here's the unsettling part. They wouldn't know they were inside a simulation. That raises a chilling question. What if we are those very characters? Sounds ridiculous, right? But is it really? Some of the brightest minds in the world take this idea seriously. Elon Musk, for example, has publicly stated that there's a 1 in a billion chance that we're living in base reality, meaning the real, non-simulated world. And he's not alone. More and more scientists and philosophers are coming to the same conclusion. To understand the first piece of evidence, we need to think about how computer simulations and virtual worlds function. Imagine you're playing a video game. As you move your character forward, the game only renders what's directly in front of you: streets, buildings, people. Everything behind you doesn't exist until you turn around. Now let's take it a step further. Think about wearing a virtual reality headset. When you look straight ahead, the world around you appears normal, but nothing behind you is loaded into existence until you turn your head. The moment you do, the headset system generates the scene in real time, while what was in front of you disappears. But here's the eerie part. How do we know something exists when we're not looking at it? What if the universe only renders things when we observe them? This brings us to one of the strangest discoveries in physics, the observer effect. You might have heard of the double-slit experiment, also known as Young's experiment. This is one of the most famous physics experiments ever conducted, and it's been repeated countless times with mind-boggling results. Here's what happens in simple terms. When scientists send light through two slits in a screen, it behaves like a wave, spreading out in all directions. But the moment they measure which slit the light goes through, something bizarre happens. The light stops behaving like a wave and acts like individual particles instead. In other words, when unobserved, light behaves one way. But the moment someone watches it closely, it changes its behavior. That might not sound too strange at first, but think about it this way. Imagine you have a cup of coffee. You look at it, and it's just a cup of coffee. But the second you look away, it transforms into the sound of ocean waves. Sounds impossible, right? Yet this is exactly what happens at the quantum level. Scientists have observed the same behavior in electrons and atoms, the very building blocks of everything we see and touch. Is our universe just a giant computer simulation? Imagine a world where certain rules govern everything, rules that cannot be broken under any circumstance. One of the most intriguing and unchangeable rules of our universe is the speed of light. No matter what we do, we can never go faster than this ultimate speed limit. It is a fundamental law of physics that nothing can exceed approximately 300,000 kilometers per second. At first glance, this might seem unfair. Why should there be such a limit? If we want to explore distant galaxies, why must we be bound by this unyielding restriction? It almost feels as if we are trapped inside some kind of programmed reality. But what if we looked at this from a different angle? Think about your smartphone or computer. Every device has a processor that operates at a fixed speed, measured in gigahertz. No matter how advanced the processor is, it has a maximum speed it cannot surpass. We accept this limitation without question because we understand that the hardware is designed this way. But when it comes to the speed of light, many people find it frustrating. Now, what if the limit of the speed of light is not a natural restriction, but a feature of a much larger system, perhaps a vast simulated reality? If our world were part of an incredibly sophisticated simulation, then the speed of light could simply represent the maximum processing speed of that system. The more we study the universe, the stranger it seems. Scientists have proven that as an object moves faster, time slows down for it. This phenomenon, called time dilation, has been confirmed through many experiments. If you were on a spaceship that could travel at the speed of light, something astonishing would happen. Imagine you set off on a journey to a galaxy 3 billion light-years away. From your perspective, you would arrive there instantly. However, for people on Earth, 3 billion years would have passed. For light particles called photons, time completely stops. A photon traveling from a distant star may have taken billions of years to reach Earth, but from the photon's perspective, no time has passed at all. This means that faster-than-light travel is impossible because time cannot slow down further than zero. But why does speed affect time? Why are space and time so deeply connected? It seems like a bizarre rule to exist in a physical universe, but it makes perfect sense in a digital one. If our reality were a simulation, then the speed of light could be a built-in limit of the system, just like a processor has a fixed clock speed. Here's another clue that suggests our reality might be more like a computer program than we think. The universe appears to be pixelated. In modern physics, there is something called the Planck length, which is the smallest possible measurement of space. It is about 1.6 times 10 to the power of negative 35 meters. Nothing in the universe can be smaller than this. It's as if space itself is made up of tiny, indivisible units, just like pixels on a screen. Not only that, but time also has a smallest possible unit, called Planck time, which is about 5.4 times 10 to the power of negative 44 seconds. This means that the universe doesn't flow continuously like a river, but instead operates in tiny, rapid flashes, like frames in a video game. If you look at a digital screen up close, you'll see that the image is made up of tiny squares or pixels. Similarly, the universe might be made up of tiny space pixels that form everything we see, but the similarities don't end there. A computer screen refreshes at a specific rate, usually 60 times per second. If the universe is a simulation, then it might also refresh, but at an unbelievably fast rate, trillions and trillions of times per second. We don't notice it because it happens far beyond human perception, just like we don't notice the flicker of a high-speed monitor. This idea raises an incredible possibility. What if reality itself blinks in and out of existence, just like a digital display? One of the strangest mysteries in physics is quantum entanglement. This occurs when two particles become linked in such a way that changing one particle instantly changes the other, even if they are on opposite sides of the universe. To understand this, imagine you have a pair of gloves. One glove is right-handed and the other is left-handed. If you send one glove to Mars and keep the other on Earth, the moment you look at the glove on Earth and see that it's right-handed, you immediately know the one on Mars is left-handed. But here's where it gets strange. With quantum entanglement, the particles don't decide their properties until someone observes them. If you check one particle and find that it is spinning in a certain direction, the other particle, no matter how far away, instantly assumes the opposite spin. This happens faster than the speed of light, which seems to break the very rules of physics. Albert Einstein called this phenomenon spooky action at a distance because it seemed impossible. However, experiments have repeatedly confirmed that quantum entanglement is real. If our universe were a giant computer simulation, this instant connection between entangled particles might be similar to how data is stored and retrieved in a digital system. In a video game, two characters can be connected by code, no matter how far apart they appear to be on the screen. Could quantum entanglement be a sign that we are living in a world where everything is connected by some hidden computational framework? A universe that follows information rules. Another fascinating detail is that physicists often describe the speed of light not just as a speed limit, but as the fastest rate at which information can be transmitted. In other words, the universe behaves like a giant information processing system. In a computer simulation, data can only be processed at a certain speed. If our reality were a digital construct, then the speed of light might simply represent the maximum data transfer rate of the system. This idea might sound like science fiction, but many scientists take it seriously. Some researchers have even suggested experiments to test whether the universe has a fundamental resolution, just like a computer screen. If they find that space and time are made up of tiny, indivisible units, it would be strong evidence that our reality is not continuous, but digital in nature. If everything we've discussed is true, it would mean that the universe is not an endless natural expanse, but a programmed environment running on an unimaginably powerful computational system. The speed of light, the pixel-like nature of space, time's strange relationship with motion, and the bizarre behavior of quantum entanglement all hint at a reality that behaves more like a high-tech simulation than a purely physical world. Scientists initially believed that entangled photons might already contain information about their spin before being measured. However, experiments inspired by Thomas Young's famous double-slit experiment, repeated and scrutinized countless times during Albert Einstein's era, revealed a surprising contradiction. These tests consistently showed that entangled photons had no predetermined spin. Instead, their spin only appeared at the moment of measurement, as if they decided their state only when observed. This seemed to support Einstein's skepticism about quantum mechanics, suggesting that something was fundamentally flawed in the theory. However, 17 years after Einstein's death, a physicist named John Bell challenged this idea with an incredibly clever and complex experiment. His goal was to test whether elementary particles truly carried hidden information about their spin before being measured. The results were astonishing. Bell's experiment demonstrated with absolute clarity that particles did not have a defined spin before measurement. Instead, they only acquired a spin the moment they were observed. In other words, before being measured, photons had no spin at all. They simply existed in a state of uncertainty. This shattered classical ideas and proved that the common comparison between quantum entanglement and pairs of gloves, where one glove is predetermined to be left-handed and the other right-handed, was completely inaccurate. What made this even more mind-blowing was that entangled particles seemed to communicate their state to each other instantly, at speeds far beyond what classical physics deemed possible. If two entangled photons were separated to opposite sides of the universe and one was measured to have an up spin, the other would immediately assume a down spin. This instantaneous reaction left physicists completely baffled. How could information travel faster than the speed of light? In the year 2008, a team of Swiss scientists from the University of Geneva set out to measure the speed of this mysterious quantum communication. They sent two entangled photons to locations 11 miles, 18 kilometers, apart. When they measured one of them, they closely monitored how quickly the second photon reacted to the change. Their equipment was sensitive enough to detect even the tiniest delay, down to speeds 100,000 times faster than light. But they found no delay at all. This suggested that quantum entanglement might not just be faster than light, it might be instantaneous. Einstein once famously argued that nothing in the physical universe could communicate instantaneously. But what if he was only wrong about the physical universe itself? What if our reality isn't purely physical, but more like a vast digital simulation? If we think of photons like pixels on a screen, the explanation becomes simpler. Imagine that two pixel-like photons become entangled through a shared program. If one pixel is assigned an up spin and the other a down spin, their program ensures they remain opposites, no matter how far apart they appear on the screen. When one photon is measured, its program selects a spin randomly, and the second photon's program instantly assigns it the opposite spin. In this scenario, distance is meaningless because the processor controlling the simulation doesn't need to physically move information. It simply updates the program's state. And if we truly are living in a computer-generated universe, this could also explain one of the biggest mysteries in science, the Fermi paradox. The paradox asks, if intelligent alien life should be common in the universe, why haven't we found any evidence of it? Perhaps the reason is shockingly simple. Maybe extraterrestrial civilizations just aren't programmed into our simulation. If that's the case, the moment we encounter alien life might not be determined by chance or science, but by the decisions of the universe's game designers. After all, in a simulation, new elements can be introduced at any time. There's a strange and puzzling phenomenon that has left many people questioning their own memories and, in some cases, even reality itself. This phenomenon doesn't belong to the world of physics or science fiction. It exists in society, in the way people collectively remember events, brands, and historical facts. It all began in the year 2009 when a woman named Fiona Broome, who calls herself a paranormal researcher, stumbled upon something shocking. For as long as she could remember, Fiona Broome had been absolutely certain that Nelson Mandela, the famous human rights activist and former president of South Africa, had died in prison during the 1980s. She was so convinced of this that she could recall news reports, newspaper headlines, and even public mourning over his death. But to her surprise, she discovered that Nelson Mandela had actually been released from prison in the year 1990 and had even served as the president of South Africa for several years before passing away in the year 2013. At first, this might sound like a simple case of one person misremembering something. However, what made it extraordinary was that Fiona Broome wasn't the only one who had this memory. When she started asking other people about it, she realized that many others also believed that Nelson Mandela had died decades before his actual passing. Some even claimed to remember watching his funeral on television and hearing his daughter deliver an emotional speech. The fact that so many unrelated people shared the same false memory led Fiona Broome to investigate further. The results of her research were astonishing. There were thousands of people across the world who remembered the exact same incorrect details. When Nelson Mandela actually died in the year 2013, these people were completely shocked. They felt as though history had somehow changed, or that they had been transported into an alternate reality where things were not as they remembered them. Fiona Broome gave this strange phenomenon a name, the Mandela effect. But as intriguing as this was, it was only the beginning. With the rise of the internet and social media, it quickly became clear that this phenomenon wasn't limited to just one historical event. Thousands of people from different countries and cultures began sharing their own experiences of memories that didn't match up with reality. Some of the most famous examples include the Volkswagen logo mystery. The logo of the famous German car manufacturer Volkswagen has a very specific design, with a small gap between the V and the W. However, thousands of people remember the logo differently, without the gap. The Monopoly man's missing monocle. Many people remember the famous mascot of the board game Monopoly, a man in a top hat, wearing a monocle. But in reality, he never had one. This has left countless people confused as they vividly recall an image that never existed, the peanut butter that was never called Jiffy. Many people swear that there used to be a brand of peanut butter called Jiffy. However, the brand has always been called Jif. It seems that people are merging the names of Jif and another peanut butter brand, Skippy, in their minds. Pikachu's tail, black tip or not. The famous Pokemon character Pikachu is remembered by many as having a black tip at the end of his tail. However, his tail has always been completely yellow, C-3PO's silver leg. In the Star Wars movies, the robot C-3PO is widely thought to be entirely gold, but in reality, he has always had one silver-colored leg. Even hardcore Star Wars fans get this detail wrong. These are just a few examples, but there are many more. What makes the Mandela effect so mysterious is that it's not just about individual people misremembering things. It's about large groups of people all sharing the exact same incorrect memory. Because so many people experience the Mandela effect, some researchers and theorists have tried to find an explanation. One of the more mind-boggling theories suggests that these memory inconsistencies might be glitches in our reality, as if we were living inside a simulated world, similar to a massive video game. This idea is linked to something called the simulation hypothesis, which suggests that our entire universe might actually be an advanced computer simulation created by a higher intelligence. This might sound like science fiction, but it's a concept that serious scientists and philosophers have considered for years. To understand why some experts believe in the possibility of a simulated reality, let's look at the rapid advancement of computer technology. In the 1940s, the world's first true programmable computer, called ENIAC, could perform about 5,000 calculations per second. That was considered groundbreaking at the time, but today, the most powerful supercomputer, called Frontier HPE Cray X235, can perform 1 quintillion calculations per second. To put that into perspective, today's fastest computer is 200 trillion times more powerful than the first one, and this has happened in less than 100 years. If computing power keeps increasing at this rate, it's not hard to imagine that in the future, humans, or some other advanced civilization, could create computer simulations so realistic that they would be indistinguishable from reality. A respected philosopher named Nick Bostrom, a professor at Oxford University, published a groundbreaking paper in the year 2003 called The Simulation Argument. In this work, he proposed that if certain conditions are true, then it is highly likely that we are living in a simulated world rather than a real one. One of the key points of his argument is about consciousness, the ability to think, feel, and be self-aware. If humans could one day create a simulation advanced enough to include people with artificial consciousness, those people inside the simulation would never know that they were not real. Think about modern video games. Characters in these games follow rules programmed by developers. But what if, in the future, those characters became so advanced that they could think for themselves? If that were to happen, how would they know that their world wasn't real? Bostrom's theory suggests that it is entirely possible that our own reality is just a highly advanced simulation created by beings far more intelligent than us. If true, then the Mandela effect could be one of the signs of small glitches or changes in this programmed reality. Over the past 80 years, computing power has increased by an almost unimaginable amount, 200 trillion times. But what if progress keeps going at this pace for another 80 years? Or even 80,000, or 80 million. That brings us right to Nick Bostrom's second assumption, that technological progress will not slow down anytime soon. For a long time, people assumed that humanity would continue advancing without hitting an obstacle that couldn't be overcome. But in recent years, some experts started to worry. A major challenge seemed to be appearing on the horizon, making futurologists question whether progress could continue at the same speed. You may have heard of Moore's law. If not, here's a quick summary. It's not really a law, but an observation made by Gordon Moore, one of Intel's founders. He noticed that computer power tended to double about every 2 years, and for decades that prediction held true with only small variations. But then, something changed. The rapid increase in computing power started slowing down. By the early 2000s, scientists noticed that making computer chips more powerful was becoming harder. Transistors, the tiny components that make computers work, could only be made so small before running into physical limitations. Signal transmission, heat production, and energy consumption all became serious challenges. As a result, creating more powerful processors became not only incredibly complex, but also extremely expensive. This led some experts to worry that we had reached the limits of what was possible. However, the tech industry didn't give up. Instead of trying to keep making processors faster in the same way, companies explored new solutions. They introduced multi-core processors, improved algorithms, and designed specialized hardware for specific tasks. And now, we stand at a groundbreaking moment. Quantum computers are no longer just an idea, they are becoming a reality. Quantum computing isn't just about more powerful machines, it represents a completely different way of processing information. The physics behind it operates on an entirely different level. And if quantum computers become widely available and affordable, they could lead to breakthroughs beyond anything we can currently imagine. Looking ahead, if quantum computing becomes as common as regular computers are today, who knows what else humanity might create? This is why Bostrom's assumption that computing power will not decline seems to make perfect sense. But here's the bigger question. What if none of this matters? What if we don't even make it far enough to see these incredible technologies develop? There's always the possibility that humanity could destroy itself before reaching its full potential. A nuclear war, an asteroid impact, or some other catastrophe could wipe us out before we become an interplanetary species. However, if we can establish human colonies on other planets, our civilization has a real chance of surviving indefinitely. That's exactly what Elon Musk is trying to achieve with his Mars mission. He wants to make sure humanity has a backup plan, and he's already made significant progress toward that goal. Now, here's where things get even more interesting. Bostrom's fourth assumption suggests that highly advanced civilizations might have a reason to create simulations, possibly even simulations of their own past. Imagine if, instead of reading history books, an advanced civilization could experience what life was like for their ancestors by running detailed simulations. Or perhaps they do it for entertainment, like an incredibly advanced version of a video game. And here's the mind-bending question. What if we are already inside one of these simulations? If a civilization far more advanced than ours had the ability to create such a realistic simulation, we might not even realize we were part of it. Imagine this. If there are countless simulated worlds, the odds that we're living in the original real world are pretty slim. It's much more likely that we're inside one of those simulations. That's the idea behind the simulation hypothesis, and it has some of the greatest minds in science seriously considering the possibility. Renowned astrophysicist Neil deGrasse Tyson explains it like this. If we can accept that it's possible to create a simulation within a simulation, then the likelihood that we're in one of these artificial realities skyrockets. Think about it. Even with today's technology, we can already create immersive virtual worlds. Now, fast forward to a future where technology is far more advanced. Imagine a world where we can generate entire digital universes, complete with characters who believe they have free will. Now picture yourself as one of those characters. You think you're making your own choices, but what if everything you experience is just a part of the simulation? Now let's say you invent a computer inside that simulation. Using that computer, you create yet another simulated world. This process repeats endlessly, creating layer upon layer of virtual realities. If you randomly threw a dart at this collection of universes, would you be more likely to hit the one real world at the beginning of it all, or one of the countless simulations that came after? The odds overwhelmingly favor the latter. Tech billionaire Elon Musk takes this theory even further. He argues that we should hope we're living in a simulation. According to Musk, civilizations either develop technology capable of creating hyper-realistic simulations, or they eventually go extinct. He believes it's far more likely that we are part of a simulation rather than existing in a raw, original reality. Philosopher Nick Bostrom, who originally formulated the simulation hypothesis, also suggests that the chances we're in a simulation are incredibly high. His argument is based on probability. If advanced civilizations are capable of creating countless simulated realities, then statistically, the odds that we're in the one true reality are close to zero. Neil deGrasse Tyson has refined his position over time. He now suggests that if humanity hasn't yet developed the ability to create hyper-realistic simulations, then we're either in the base reality, the original universe, or in the last simulation at the end of a long chain. That would mean we have a 50-50 chance of being real or simulated. The difficulty in proving or disproving the simulation theory was highlighted by philosopher David Chalmers. He pointed out a major problem. If we are in a simulation, then the creators of that simulation could easily manipulate any evidence we find. In other words, even if we try to test our reality, the results could be programmed to mislead us. In space science, dark matter is a strange and hidden type of material that we can't see because it doesn't react with light or any other kind of energy. We know it is there because of the odd way it affects gravity, which can't be fully understood using the known rules of physics unless there is more material around than we can actually see. These strange effects appear when we look at things like how galaxies form and change over time, how light bends around huge objects, called gravitational lensing, and even the way galaxies move inside groups. We also see its impact on how the universe is shaped and the leftover energy from the Big Bang, the cosmic microwave background. In the most widely accepted explanation of the universe called the Lambda CDM model, all the mass and energy in the universe is made up of 5% normal material, the kind we can see, 27% dark matter, and 68% dark energy. That means dark matter makes up about 85% of all mass, while dark matter and dark energy together make up 95% of all energy in the universe. We don't know exactly what dark matter is, but it doesn't seem to interact with regular material or light, except through gravity, making it almost impossible to find with the tools we have today. The main idea is that dark matter might be made up of tiny, unknown particles, such as weakly interacting massive particles, WIMPs, or axions. Another idea is that dark matter could be made of ancient black holes from the early universe. Dark matter can be divided into different types based on how fast its particles move, cold, warm, or hot. Most experts believe dark matter is cold, meaning its particles move slowly, allowing them to gather together and form structures over time. While most space scientists think dark matter exists, some still have doubts. A small number of researchers, confused by certain findings that regular dark matter doesn't completely explain, suggest that maybe the laws of gravity need to be changed. They have suggested new ideas like modified Newtonian dynamics or different types of gravity, but none of these ideas can perfectly explain all the facts we have found so far. This means that even if gravity needs some updates, dark matter still seems to be an important part of the mystery. The idea of dark matter has a long and exciting history, full of surprising discoveries and ideas that helped build what we know today about the universe. The story begins with the work of some of the greatest minds in science, starting in the late 1800s. In 1884, William Thomson, better known as Lord Kelvin, made some interesting discoveries. He talked about the possible number of stars around our sun in a book based on a series of talks he gave in Baltimore. Kelvin was trying to guess the number of stars near the sun by studying how stars move in space. Using this data, he wondered what would happen if there were 1 billion stars within a distance of about 3,200 light-years from the sun. At this distance, the stars would seem to move in ways that were difficult to explain, and this idea led to more thoughts about hidden material in space. Lord Kelvin also guessed that the sun's age was between 20 and 100 million years, which was later proven wrong. But his interest in stars and their movements helped shape early ideas about dark matter. A few decades later, in 1906, the French scientist Henri Poincaré used the term dark matter or matière obscure while discussing Lord Kelvin's work. Poincaré suggested that the universe might have hidden material, but he also thought it would be much less than the visible material we can see. Even though his ideas were not correct, Poincaré's mention of dark matter helped introduce the idea into scientific discussions. In the 1920s, dark matter continued to be a mystery for space experts. In 1922, Dutch astronomer Jacobus Kapteyn became one of the first to use the speeds of stars to suggest that dark matter might exist. He noticed that the way stars move could be affected by unseen forces, hinting at the presence of hidden material. Then, in 1930, Swedish scientist Knut Lundmark built on this idea, realizing that the universe must have far more mass than what we can observe through telescopes. This was a major discovery because it suggested that the visible universe might not be the whole picture. In 1932, another Dutch scientist, Jan Oort, added to the discussion by suggesting that dark matter might be present in our galaxy. Oort studied the movement of stars near our galaxy and concluded that there had to be more mass in the Milky Way than what we could see. However, he later found that his calculations were not entirely right, and more studies would be needed to truly understand this invisible material. Then, in 1933, Swiss space expert Fritz Zwicky made an important discovery while studying galaxy groups at the California Institute of Technology. Zwicky was researching the Coma cluster, a huge collection of galaxies, and noticed something odd. The galaxies in the cluster were moving much faster than expected based on the visible material. This led him to suggest that there must be a large amount of unseen material, which he called Dunkelmaterie, dark matter. Zwicky estimated that the Coma cluster had about 400 times more mass than what telescopes could detect, based on how the galaxies were moving. He believed this hidden mass was responsible for the gravity that held the galaxy cluster together. Although Zwicky's estimates were very inaccurate, mostly because of old data, he was one of the first to correctly identify that the universe must contain unseen material that pulls on objects with its gravity. Zwicky, however, had a different idea about dark matter than we do today. He thought dark matter was just normal matter that didn't give off light, instead of something completely different, like the mysterious dark matter we think of now. Still, his research was an important first step toward discovering dark matter. As time passed, more proof that dark matter existed started to show up. One of the main pieces of this proof came from studying how galaxies rotate. In the year 1939, H.W. Babcock studied how the Andromeda Galaxy, the closest spiral galaxy to us, spins. He found that the stars near the edges of the galaxy were moving much faster than they should have been. This meant that there had to be a lot more mass in the galaxy than what was visible. At first, Babcock suggested that the strange rotation might be caused by light being absorbed inside the galaxy, or that the way the galaxy moved was different at the edges. But his findings were an early clue that something invisible was affecting the galaxy's movement. The next year, in 1940, Jan Oort made another major discovery. He studied a galaxy called NGC 3115 and found a huge, unseen cloud of mass around it. This was another sign that galaxies might have hidden matter beyond what we could detect with our tools at the time. The idea of dark matter really started to gain attention in the 1970s. Different discoveries were put together, leading scientists to believe that galaxies might be surrounded by large, invisible halos of matter. In the year 1974, two separate teams, one from Princeton, New Jersey, led by Jeremiah Oestreicher, Jim Peebles, and Amos Yahill, and another from Tartu, Estonia, led by Jan Einasto, N. Saar, and Ants Kasik, came to the same conclusion independently, making the idea even stronger. One of the biggest clues that these invisible halos existed was how galaxies rotated. Both regular telescopes and radio telescopes helped reveal this. Vera Rubin and Kent Ford, using a new type of telescope tool, took more precise measurements of how fast spiral galaxies were spinning, and their results were surprising. At the same time, radio astronomers used better radio telescopes to study atomic hydrogen at a wavelength of 21 centimeters in nearby galaxies. Unlike starlight, which can only be seen in the middle of galaxies, hydrogen gas spreads out much farther. This let astronomers study rotation patterns at greater distances, giving them a better idea of how much total mass a galaxy had. Early research on the Andromeda galaxy, using giant telescopes like the 300-foot Green Bank telescope and the 250-foot Jodrell Bank telescope, showed that the hydrogen rotation curve didn't match what was expected based on Kepler's laws, which explain how objects should move around a center of gravity. As technology improved, more advanced equipment allowed scientists to take even better measurements. In the year 1975, Roberts and Whitehurst made further progress by measuring how fast Andromeda was spinning all the way out to 30,000 parsecs. Their results showed that the galaxy's rotation curve stayed flat even at far distances. This was a big deal because it suggested that there was much more mass in the galaxy than what could be seen with regular telescopes. Their charts combined data from visible light and hydrogen, clearly showing that the outer edges of the galaxy were rotating in an unexpected way. At the same time, scientists were coming up with even better methods to study galaxies. Using groups of radio telescopes working together, researchers like Rogstad and Shostak in the year 1972 mapped the hydrogen rotation curves of 5 spiral galaxies. They found that all these galaxies had flat rotation curves too, which meant that there was more mass in the outer areas than what could be explained by visible stars and light. By the late 1970s, most scientists accepted that dark matter halos likely surrounded galaxies, and this became one of the biggest unanswered questions in astronomy. In the 1980s and 1990s, more and more studies supported the idea that dark matter was real. One major study, done by Persic, Salucci, and Stell in the year 1996, analyzed 967 spiral galaxies and found strong proof of dark matter's existence. Other supporting evidence included strange effects like gravitational lensing, where light bends around galaxy clusters, how hot gas is spread out in galaxies, and the way tiny temperature changes show up in the cosmic microwave background, the leftover heat from the Big Bang. Today, most scientists agree that dark matter is made up of particles we haven't discovered yet, and these particles are unlike anything we know. Finding these mysterious particles has become one of the biggest challenges in physics, with many scientists using different experiments to try and solve the mystery. In simple terms, when scientists talk about matter in the universe, they mean anything that adds to the total energy, and its density changes in a specific way as the universe gets bigger. Specifically, as the universe stretches, matter spreads out and becomes thinner. This is different from radiation, which fades away even faster. Its energy weakens more as the universe expands. On the other hand, the cosmological constant behaves differently. It stays the same no matter how much the universe grows, meaning its energy density does not change. This difference in how matter, radiation, and the cosmological constant behave is due to something called radiation redshift. To understand this, imagine the universe expanding. If the size of the visible universe doubles, the scale factor of expansion also doubles. Because of this, the energy of things like the cosmic microwave background radiation, the leftover glow from the Big Bang, gets weaker, since each photon, light particle, has to spread out over a larger space, reducing its energy. The same happens to fast-moving particles like early neutrinos. They lose energy the same way. But the cosmological constant, since it is a part of space itself, stays the same no matter how much the universe expands. As for dark matter, this term generally refers to parts of the universe that we cannot see but still have weight and follow similar rules to regular matter. However, in more specific terms, dark matter is often used to describe a special kind of unseen matter that isn't made of the usual tiny building blocks we know, except for something called missing baryons. Depending on the situation, the meaning of dark matter can change. The arms of spiral galaxies spin around their center, and as you move farther from the center, the amount of visible matter in the galaxy becomes smaller. If all the galaxy's weight were visible, it would act like a simple system where most of the weight is gathered in the center and objects would circle around it, much like how planets go around the sun in our solar system. Based on Kepler's third law, we would expect the speeds of these objects to slow down the farther they are from the center, just like how planets in our solar system move slower the farther they are from the sun. But that's not what actually happens in galaxies. Instead, the spinning speeds of stars and gas in a galaxy stay the same or even increase the farther they are from the center. To explain this strange behavior, it seems clear that the way weight is spread out in spiral galaxies is different from how it is in the solar system. In particular, there may be a huge amount of invisible matter, what we call dark matter, around the edges of the galaxy. In tightly connected systems like galaxies, the stars also follow a rule called the virial theorem, which helps explain how weight is spread out based on how fast the stars move. When astronomers check the speeds of stars in systems like round galaxies or crowded star clusters, they can use this rule to figure out how weight is distributed. However, in many cases, the measured speeds don't match what we'd expect based on the amount of visible matter in the system, even when we consider the complicated ways stars move. Just like with the spinning speeds of galaxies, the most reasonable answer to this mismatch is that there's more unseen matter involved. Again, dark matter. Groups of galaxies are important for studying dark matter because we can measure their weight in three ways: by checking how fast the galaxies in the group move, by studying the X-rays given off by the hot gas inside the group. By analyzing these X-rays, we can figure out the heat and thickness of the gas, which helps us calculate the pressure. Using the balance between gravity and pressure, we can find out the total weight of the group. Through gravitational lensing, where the weight of the group bends light from objects that are even farther away. This lets us measure the group's weight without needing to directly study the motion of the galaxies. All three of these methods lead to the same conclusion. Dark matter makes up about 5 times the weight of all the visible matter in these groups. One interesting result of Einstein's theory of general relativity is a process called gravitational lensing. This happens when very heavy objects like galaxies or groups of galaxies sit between a light source and the person observing it. These heavy objects work like a lens, bending the light that passes through them, which makes the light from the source look distorted. The key thing to know is that gravitational lensing only needs weight to happen. It doesn't matter what the weight is made of. The heavier an object is, the stronger the bending of light will be. For example, imagine a group of galaxies lying between a faraway object like a quasar and us. In this case, the galaxies in the group will bend the light from the quasar, making it look different. When we talk about strong lensing, we mean the extreme way light from galaxies in the background can be bent into arc shapes as it moves through a heavy object's gravitational field. This has been seen around many faraway galaxy groups, including one called Abell 1689. By studying the shape of these arcs, scientists can figure out the weight of the galaxy group causing the bending. In the weak lensing case, the bending is much less obvious, and galaxies don't turn into arcs. Instead, we see tiny changes in the shapes of galaxies. By looking at these small changes, scientists can learn about how dark matter is spread throughout the universe. The patterns of weight and light from these observations match what we expect from dark matter studies. Now, while both dark matter and regular matter are types of matter, they act very differently. In the early universe, regular matter had an electric charge and reacted strongly with light, which caused it to spread out. Dark matter, on the other hand, doesn't interact directly with light, but it still affects the universe in other ways. For example, it influences the cosmic microwave background, CMB, through its gravity, especially on large scales. It also affects the movement and thickness of regular matter. Because of these differences, regular matter and dark matter develop in separate ways and leave clear signs on the CMB. The CMB is very close to being a perfect type of radiation, meaning it gives off an even temperature everywhere. However, there are tiny temperature differences, about 1 part in 100,000, that scientists can study. These small variations, called anisotropies, can be mapped out across the sky. When scientists turn this map into a graph called the angular power spectrum, they see a series of peaks that are evenly spaced but have different heights. The exact positions of these peaks depend on key parts of cosmology, and by comparing these positions to theory, we can learn more about what makes up the universe. The first discovery of the CMB's anisotropies was made in 1992 by the COBE satellite, but the image was not sharp enough to see the detailed peaks. In 2000, the Boomerang experiment, using a balloon to take measurements, found the first of these peaks. Later, the WMAP satellite and the Planck spacecraft measured these peaks much more accurately. Their discoveries supported the lambda CDM model of cosmology. The formation of structures in the universe began shortly after the Big Bang, when small, uneven spots in the universe's density caused matter to collapse and create stars, galaxies, and groups of galaxies. Before this time, the universe was smooth and even, with no major differences in density, as explained by the Friedmann equations in general relativity. Over time, tiny differences in density started to grow and gather together, turning the smooth and empty universe into a more complex one filled with stars and galaxies. In the beginning, radiation controlled the universe and played a big role in shaping matter. This radiation stopped normal matter from clumping together to form structures. If the universe only had normal matter, these small differences wouldn't have had enough time to grow into the galaxies and clusters we see today. The answer to this problem is dark matter, which is not affected by radiation. Because of this, its density differences were able to grow first, forming gravitational wells that later pulled in normal matter, helping it collapse into galaxies and other cosmic structures. The pull of dark matter worked like a magnet, attracting normal matter and speeding up the formation of these giant space objects. A clear example of dark matter's effect is the Bullet cluster, created by the crash of two huge galaxy clusters. What makes the Bullet cluster so important is the gap between where its mass appears based on the bending of light, gravitational lensing, and where the visible matter is located. This gap is hard to explain using alternative gravity theories, which assume that light bending should only happen around visible matter. However, the usual dark matter theory explains this easily. The visible gas in the clusters, which interacts with light and radiation, was slowed down and cooled by electromagnetic forces during the crash. Dark matter, however, does not interact with light the same way, so it passed through the crash without being affected, moving away from the visible gas. This created two separate lensing peaks, which scientists observed. Besides dark matter, astronomers use Type Ia supernovae as standard candles to measure distances across the universe. These supernovae have a known brightness, so by checking how dim they look, scientists can figure out how far away they are. This method showed that the universe is expanding at an increasing speed, something that is usually linked to dark energy. Baryon acoustic oscillations, BAO, are regular patterns in the density of normal matter, baryons, in the universe, which happened on a big scale in the early universe. These patterns were caused by sound waves moving through the hot, thick mix of photons and baryons before the universe cooled enough for atoms to form. The effects of these sound waves can still be seen in the cosmic microwave background, CMB, radiation. As the universe got bigger, dark matter and normal matter started clumping together, but the effect of these early patterns faded over time. Still, scientists can see a slight tendency for galaxies to be spaced about 147 million light-years apart, which is a small but noticeable sign of these early patterns. This effect was predicted in the early 1990s and confirmed in 2005 through large galaxy surveys like the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey. By combining CMB observations with BAO measurements, scientists can get an exact estimate of key cosmic values, such as the universe's expansion rate and the amount of matter it has. These findings support the lambda CDM model, the most widely accepted theory of the universe's structure and evolution. Large surveys of galaxy redshifts help us make a three-dimensional map of how galaxies are spread across space. However, these maps are not perfect because the distances we estimate are based on the redshift we see. The redshift we measure is influenced by two things, mainly the universe's expansion, but also a smaller effect from the galaxy's own movement, known as its peculiar velocity. In general, superclusters, large groups of galaxies, are growing more slowly than the universe as a whole because their gravity is pulling things together. Meanwhile, the vast empty spaces between galaxies, called voids, are expanding faster than the universe itself. This difference in movement creates interesting effects. For example, galaxies in front of a supercluster move toward it faster than expected, making their redshift slightly higher than it should be based on their distance. In contrast, galaxies behind the supercluster appear to have a slightly lower redshift than expected. This difference makes superclusters look flattened along our line of sight, while voids appear stretched. However, this effect is hard to see in a single structure because we don't know its true shape. Instead, scientists noticed this pattern by averaging data from many structures. This effect was first predicted by Nick Kaiser in 1987 and later confirmed in 2001 by the 2DF Galaxy Redshift Survey, with results matching what the Lambda CDM model predicts. In a related area of study, the Lyman alpha forest refers to the set of absorption lines seen in the light from faraway galaxies and quasars. These lines come from neutral hydrogen absorbing light at a specific wavelength, called the Lyman alpha transition. Studying the Lyman alpha forest helps astronomers test and improve cosmic models, with results that match findings from the WMAP data. Dark matter is divided into three types: cold, warm, and hot. These terms do not refer to temperature but instead describe how fast the particles moved in the early universe. Simply put, they describe how far the particles traveled due to random motion before the universe started expanding and slowing them down. This distance is called the free streaming length, FSL. Dark matter is classified based on how this FSL compares to the size of a protogalaxy, an early cosmic object that later became a small galaxy. If the FSL is much smaller than a protogalaxy, it is called cold dark matter. If the FSL is about the same size as a protogalaxy, it is warm dark matter. If the FSL is much bigger, it is hot dark matter. Some theories suggest a mix of these types, which were more popular in the middle of the 1990s, but lost support after dark energy was discovered. The main idea behind the free streaming length is that after the Big Bang, the universe started with small density differences caused by tiny quantum changes at the smallest levels. As these particles moved from denser areas to less dense ones, the rapid growth of the universe set a limit on how far they could travel. Faster particles, like those in hot dark matter, could travel farther before the universe expanded too much, while slower particles, like those in cold dark matter, did not move as far. This means the free streaming length sets a limit on the size of structures that could form in the early universe. Hot dark matter would lead to the creation of large structures, like superclusters, which would later break apart into galaxies. On the other hand, cold dark matter allows smaller structures like galaxies to form first. Recent studies, especially deep space images of the universe, show that galaxies formed first, followed by groups of galaxies and even larger collections as they came together. This supports the idea that most dark matter is slow-moving rather than fast. This is also why neutrinos, which move almost as fast as light and would be considered fast dark matter, cannot make up most of it. Dark matter refers to any kind of matter that mainly affects visible things like stars and planets through gravity. This means that dark matter might not be a completely different kind of particle, but could, in theory, include regular matter like protons or neutrons. In fact, many objects that astronomers are familiar with, such as planets, failed stars, brown dwarfs, small stars, red dwarfs, regular stars, old fading stars, white dwarfs, collapsed stars, neutron stars, and black holes, belong to this category. For example, when a black hole pulls in matter, it doesn't distinguish between regular matter, like protons and other types. Once inside, everything is treated the same. These difficult-to-detect objects are called machos, massive compact halo objects. Some scientists once believed that machos made up most dark matter, but this idea has mostly been ruled out. There is strong proof that most dark matter is not made of ordinary, visible material. First, if there were enough normal matter, like gas or dust, spread around, we would be able to see it when starlight shines on it. But we don't see this much matter. Next, the Big Bang theory explains how the elements we see today were created. According to this theory, if the early universe had more regular matter, called baryons, we would see a higher amount of elements like helium, lithium, and heavier elements. From what we observe, we know that only about 4 to 5% of the universe's total mass is made of this regular matter. However, large studies of galaxies and other space structures show that the total amount of matter is about 30% of what is needed to keep the universe balanced. Further research has shown that only a small part of dark matter seems to be made of ordinary hidden objects like small planets or black holes, machos. Studies that look at how gravity bends light, gravitational microlensing, suggest that these objects cannot explain most of dark matter because their sizes fall within a range that rules out almost all possible candidates. Detailed studies of the faint radiation left over from the Big Bang, cosmic microwave background, using missions like WMAP and Planck, provide strong proof that about 5/6 of the matter in the universe does not interact much with light or regular matter except through gravity. This suggests that dark matter is mostly invisible and can only be detected by how its gravity affects things around it. If regular matter, baryonic matter, does not make up most of dark matter, then dark matter must be made of something else called non-baryonic matter. There are two main possibilities for this: new, unknown particles and very old black holes from the early universe. Unlike regular matter, these unknown particles did not help create the elements that formed after the Big Bang, a process called Big Bang nuclear synthesis. Instead, we only notice them because of their gravitational effects, such as bending light, called weak lensing. Some types of dark matter might even interact with each other, self-interacting dark matter, or with regular particles like WIMPs, weakly interacting massive particles. These interactions might create detectable signals, such as gamma rays and neutrinos, which scientists could possibly observe in direct detection. There are many possible types of dark matter, each with advantages and problems. WIMPs do not have a strict definition, but they are generally thought to be tiny particles that interact through gravity and possibly other weak forces, such as the weak nuclear force. Many theories suggest that WIMPs were created in the early universe in a way similar to regular particles. These particles would form what is known as cold dark matter. To explain the amount of dark matter we have today, WIMP particles would need to destroy each other in a specific way. This matches what would happen if they had masses around 100 billion electron volts and interacted through the weak force. This idea is often called the WIMP miracle because it fits so well with theories that expand the standard model of particle physics. A stable partner particle from these theories has long been considered a strong possibility for dark matter. Scientists are working hard to find WIMPs by looking for the results of their destruction, such as gamma rays, neutrinos, and cosmic rays from nearby galaxies. They also run experiments in labs to try to detect WIMPs by measuring how they interact with atomic nuclei, or by trying to create them in powerful machines like the Large Hadron Collider. However, in the early 2010s, experiments did not find strong proof of these particles, and results from the collider raised doubts about the simplest WIMP ideas. Axions, another possible type of dark matter, are theoretical particles first suggested in 1978 by Frank Wilczek and Steven Weinberg. These particles were originally proposed to solve a problem in the theory of how tiny particles, quarks and gluons, interact. Axions are extremely light and rarely interact with other particles, making them a strong candidate for dark matter. They could have been created in the early universe and would still exist today, depending on their mass. Axions are believed to be so light that they could help solve some of the small-scale problems in the leading cosmological model, lambda CDM. The axion idea has become more popular in recent years, especially since WIMPs have not been detected. Because axions have such a low mass, their quantum effects could help explain small-scale dark matter mysteries. Another interesting idea is that dark matter could include ancient black holes, called primordial black holes, which may have formed right after the Big Bang. During the period of rapid expansion called inflation, extremely dense regions of tiny particles could have collapsed under their own gravity, creating black holes without needing a dying star, as regular black holes do. These black holes would have existed before the first stars formed and could be as small as atoms or much larger than typical black holes formed by collapsing stars. The idea of tiny black holes from the early universe was first proposed in 1967 by Yakov Zeldovich and Igor Novikov, and later by Stephen Hawking in 1971. The theory quickly became popular as a possible reason for dark matter. One reason why these black holes were considered a good match for dark matter is that scientists already understand how black holes work based on general relativity, and we already know that black holes exist. However, forming these tiny black holes may need very special conditions, like unusual cosmic expansion or ideas that go beyond the standard rules of particle physics. In 2015, scientists detected gravitational waves from black holes merging, which brought renewed attention to these early black holes as a possible source of dark matter. Some of the black holes found in these studies were heavier than expected, based on normal ways black holes form, such as when a star collapses. This led some experts to think they might be early universe black holes. But later research looking for signs of gravitational bending of light by these black holes found no proof of their existence. Some scientists argue that this might be due to incorrect guesses about their size. Future observations, including those from the James Webb Space Telescope, may provide clearer answers. At one point, scientists thought that extremely tiny black holes could make up a large part of dark matter. However, data from the Voyager 1 spacecraft, which traveled beyond the Sun's influence, showed unexpected results. It measured the flow of small charged particles and found fewer than expected, with energy levels that did not match predictions. This led experts to believe that these tiny black holes are too rare to explain dark matter. Even with this, the idea of very dense dark matter is still being studied, and new theories are exploring ways dark matter might cool down. As of 2018, the mystery of dark matter remains unsolved. In 2019, more studies of the Andromeda galaxy showed no signs of gravitational bending of light, which should have been present if small black holes were there. This added more doubt about their existence. However, there is still much we don't understand. There is a size range smaller than what we can currently observe using light-based methods, where tiny black holes could still make up dark matter. This remains an open area of study that continues to challenge our understanding of space. If dark matter is made of particles that barely interact with anything, an important question arises. Could these particles form objects like planets, stars, or black holes? Historically, the answer has been no, and there are two main reasons for this. It can't easily lose energy. Normal matter forms stars and planets because it can lose energy in different ways. For example, when particles move toward the center of gravity, they lose energy, allowing them to slow down and come together into stable objects. Dark matter, however, does not seem to have a way to lose energy. It only reacts with gravity and does not strongly interact with other matter. Without a way to release energy, dark matter particles pulled inward would just heat up, move faster, and escape, preventing them from forming solid objects. It doesn't interact in many ways. Regular matter interacts through different forces, like gravity, electromagnetism, and the strong nuclear force. This allows it to create complex things like atoms, stars, and galaxies. For example, inside stars, particles interact through nuclear reactions, producing light and tiny particles called neutrinos. With dark matter, we don't see these types of interactions. It only interacts through gravity, and possibly weakly in other ways, but this is uncertain. Because of this, dark matter cannot form the kinds of objects that normal matter does. If dark matter is made of tiny subatomic particles, they could pass through every square centimeter of Earth millions or even billions of times each second. Many experiments are testing this idea. While weakly interacting massive particles, WIMPs, have been the most studied, axions are also being researched, especially in projects like the Axion dark matter experiment. Other ideas include heavier particles from an unknown sector of physics that only interact with regular matter through gravity. There are two main types of experiments studying dark matter. Direct detection experiments. These look for tiny interactions between dark matter and atoms inside a detector. The goal is to detect small energy changes, a few thousandths of an electron volt, caused by these interactions. If dark matter collides with an atom, the atom might release energy in the form of light or vibrations, which can be measured. To avoid interference from background noise, these experiments are often done deep underground, where cosmic rays cannot reach. Important underground labs include Stawell Mine, Sudan Mine, and the Gran Sasso National Laboratory. These experiments use two main technologies: supercooled detectors that measure heat from particle collisions in materials like germanium, Liquid detectors that detect flashes of light when particles hit liquids like xenon or argon. Well-known experiments using these methods include CDMs, CREST, xenon, and LUX. These detectors are very good at separating dark matter signals from background signals, since dark matter is expected to interact differently than normal particles. Indirect detection experiments. These look for the side effects of dark matter particles destroying or breaking apart. So far, no direct evidence of dark matter has been found in these tests, but they have helped scientists narrow down possible explanations. One interesting claim comes from the Dama NAI and Dama Libra projects, which noticed a yearly pattern in their data, possibly due to Earth moving through a cloud of dark matter. However, other experiments such as LUX and super CDMs have not seen the same effect, making the claim uncertain. Some experiments also try to track dark matter's movement based on how the solar system moves through the galaxy. These tests, such as DMTPC and drift, try to find out the direction of dark matter's motion, helping to separate real signals from background noise. Indirect detection experiments also look for unusual signals from places in space with a lot of dark matter, like the center of the Milky Way. If two dark matter particles collide, they might destroy each other, releasing high-energy light or pairs of regular and antimatter particles. If dark matter particles are unstable, they might slowly break down into normal particles, which could be detected as unexpected bursts of gamma rays, antimatter, or high-energy particles. However, since other space events can produce similar signals, multiple detections are needed to confirm dark matter. Some dark matter particles might also get trapped inside stars or planets, where they could collide and destroy each other, releasing a burst of high-energy neutrinos. This could be strong evidence of dark matter made of WIMPs. Experiments like Amanda, IceCube, and Antares are searching for these signals. Also, in 2015, the discovery of gravitational waves by LIGO opened new ways to study dark matter, especially if some of it exists as tiny black holes. Several experiments have looked for dark matter signals. In 2008, the Energetic Gamma Ray Experiment telescope saw more gamma rays from the Milky Way than expected, but scientists thought this was due to mistakes in the telescope's sensitivity. In 2009, the Fermi Gamma Ray Space Telescope found an unexpected increase in gamma rays from the Milky Way's center, which could be from dark matter or an unknown group of stars. In 2012, more Fermi data showed a 130 billion electron-volt signal, which some thought could come from dark matter. At even higher energy levels, ground-based telescopes have searched for dark matter signals in small galaxies and galaxy clusters. In 2006, the Pamela experiment found an unusual number of positrons, which might come from dark matter or pulsars. However, it did not find a similar increase in antiprotons. In 2013, the Alpha Magnetic Spectrometer on the International Space Station observed high-energy cosmic rays that might be linked to dark matter. Another way to find dark matter is by trying to create it in a lab. Scientists at the Large Hadron Collider, LHC, search for dark matter particles formed in proton collisions. Since dark matter barely interacts, it could be identified by measuring missing energy and momentum in particle collisions. The LEP experiment also tested dark matter interactions with electrons. If dark matter is found in these experiments, it must also be confirmed through direct or indirect detection. Because dark matter remains unidentified, alternative theories exist. Some scientists suggest modifying the laws of gravity instead of needing dark matter. Ideas like MOND, TVES, negative mass, and dark fluid attempt to explain cosmic mysteries without dark matter. However, most scientists believe dark matter must exist since its effects are seen in many different ways. The universe is full of mysteries, but some stars stand out as true anomalies. One such celestial body is hidden in the vast expanse of the Centaurus constellation. This region of the sky is home to Alpha Centauri, a well-known star system consisting of 3 stars. However, beyond these familiar celestial objects lies something even more extraordinary, a peculiar and baffling star called Chabil star. This star is unlike any other. It is massive, weighing 4 times the mass of our Sun, and is located 365 light-years away from Earth. Most stars function like enormous thermonuclear reactors, fusing lighter elements into heavier ones at their cores. But Chabil star defies this norm. It produces elements that scientists never expected to find inside a star, and some of these elements might not even exist in nature, or at least not yet. Chabil star, scientifically known as HD 10165, is so bizarre that some researchers have jokingly referred to it as plutonium star. This is because it appears to contain large amounts of plutonium along with other incredibly heavy elements. These elements are highly unstable and decay quickly, so quickly that they should not exist in a star at all. There are only a few possible explanations for this strange phenomenon. There are natural elements in the universe that we have not yet discovered. Scientists were wrong about the existence of super-heavy elements. An intelligent alien species artificially created these elements and dumped them into the star. Every star emits light, and by analyzing this light, astronomers can determine which elements are present within the star. This is done by studying something called the spectral signature, a kind of chemical fingerprint that reveals what the star is made of. But when researchers observed Chabil star's spectrum, they found something shocking. Instead of a clear and organized pattern of elements, its spectral signature was chaotic and unlike anything seen before. Some astronomers even described it as an infinite number of lines, making it almost impossible to analyze. This was the first clue that something unusual was happening inside this star. Scientists have been observing Chabil star since the 1960s, yet they are still unable to fully determine what it is composed of. One possibility is that the star contains elements that have never been discovered before, elements that exist only inside this celestial anomaly. One of the most baffling things about Chabil star is that it contains almost no iron. This is incredibly strange because iron is a very common element in stars. Most stars generate energy by fusing lighter elements into heavier ones, and this process usually leads to the formation of iron. The fact that Chabil star lacks iron suggests that something completely different is happening inside it. At the same time, the star is rich in lanthanides, a group of rare elements that include substances like europium and samarium. These elements are normally found only in tiny amounts in most stars, yet Chabil star contains them in abundant quantities. Even more mysteriously, researchers have detected atoms of promethium and plutonium, two elements that should not exist inside a star for very long. Promethium has a half-life of less than 20 years, meaning that it should decay rapidly. Plutonium has a maximum half-life of 24,000 years, which is still extremely short when compared to the lifespan of a star. This means that if these elements were naturally present in the universe, they should have completely disappeared long before humans ever invented telescopes. Yet somehow they still exist in Chabil star. Scientists have proposed several theories to explain this mystery, but none of them are completely satisfying. Supernova theory. Some astronomers suggest that these elements were created when a nearby star exploded in a supernova, scattering unusual materials into space, which then became part of Chabil star. However, there is little evidence to support this idea. Neutron star reactions. Another theory is that a nearby neutron star might be triggering nuclear reactions inside Chabil star, creating new elements. However, no neutron stars have been found in the area, undiscovered super-heavy elements. A more radical possibility is that Chabil star contains unknown elements that scientists have never identified before. These mysterious elements might be breaking down into more familiar but short-lived isotopes, which is why we can see traces of plutonium and promethium. Some of the hypothetical elements that might exist in Chabil star include flerovium, ununenium, and unberyllium, substances that scientists have only been able to create in laboratories in microscopic amounts. If these elements naturally exist inside Chabil star, it would revolutionize our understanding of chemistry and nuclear physics. There is also a fascinating theory that Chabil star might be part of something called the Island of Stability. The Island of Stability is a theoretical group of super-heavy elements that are incredibly stable, unlike most other heavy elements, which decay quickly. Scientists have been searching for these stable elements for years, but they have never been found. As if its chemical composition wasn't strange enough, Chabil star also behaves unusually. Most stars move through space in predictable patterns, but Chabil star appears to follow an odd and unexplained trajectory. Some researchers have even speculated that an unknown force might be acting on the star, though there is no solid evidence to confirm this yet. With so many mysteries surrounding Chabil star, some scientists have considered the possibility of alien involvement. Scientists have recently taken a closer look at a fascinating star, and what they found is nothing short of bizarre. A research team from the Libetz Institute for Astrophysics in Potsdam, along with experts from Germany, has discovered that the star known as HD 11065 is not just made of unusual materials, it also moves in an incredibly strange way. A separate team of scientists from Chile made an even more astonishing discovery. The star takes a whopping 188 years to complete a single rotation. That's nearly 2 human lifetimes for just one full spin. According to their analysis of newly gathered and historical magnetic field data, this makes HD 11065 one of the slowest rotating stars ever observed. While it's true that some types of stars, like AP stars, tend to rotate slowly, this particular one is extreme, even by those standards. Interestingly, some researchers have raised the possibility that we may have misunderstood parts of the star's chemical composition. Originally, scientists believed it contained short-lived isotopes, but that assumption may not be correct. What's even more puzzling is its spectral signature. Typically, when studying stars, scientists can see distinct lines in their spectra that represent different elements. But with HD 11065, these lines appear everywhere, making it incredibly difficult to identify exactly what elements are present. This mystery has led to a long-running debate in the scientific community, one that still has no clear answers. Among the many theories is a rather controversial yet intriguing one. Some researchers believe the star's composition is eerily similar to the byproducts of artificial nuclear reactions. This idea was first suggested in the year 1980 by American scientists Daniel Whitmire and Jason Wright. They proposed that advanced extraterrestrial civilizations might use stars to dispose of their nuclear waste. In fact, they even speculated that Type A stars, like HD 11065, would be the most likely places to find this kind of material. If this theory is correct, then the presence of certain short-lived elements on the star could actually be evidence of alien technology. Of course, the scientific community remains divided on this idea. Even if this star isn't proof of extraterrestrial activity, understanding its chemical makeup could still be groundbreaking for astrophysics. More recently, researchers have proposed a different explanation for the star's strange elements. They believe a nearby neutron star might be influencing HD 11065, altering its atmosphere. This hypothesis sounds reasonable, except for one major problem. There are no neutron stars anywhere near it. Scientists from the University of South Wales have another intriguing idea. They suggest that the actinides found in HD 11065 could be the result of slow decay from super-heavy elements. This is based on the concept of a so-called island of stability, a theoretical group of elements with over 114 protons in their nucleus. These super-heavy elements could be long-lived, and their gradual breakdown might explain the presence of short-lived elements like plutonium and einsteinium on the star. If this theory is correct, then HD 11065 could be home to an entirely new isotope, one that exists naturally in the universe but has never been discovered before. If that sounds far-fetched, consider this. Helium was first discovered on the Sun before it was ever found on Earth. There's no doubt that this star is one of the strangest objects ever observed in space. Its secrets will likely puzzle scientists for years, possibly even centuries. Unless, of course, someone from the future decides to travel back in time and finally reveal what's really going on with this extraordinary star. Time travel paradoxes. https://u2.b/e1 ctm9_c2fq?si=lios 55uv1g_6 mjk5. Have you ever wondered what would happen if you traveled back in time and did something that changed the course of history? What if you prevented your own grandparents from meeting? Or what if, in some bizarre twist of fate, you became your own father? It sounds like something straight out of a science fiction movie, but these ideas have been puzzling not only science enthusiasts, but also some of the greatest minds in the world, including Nobel Prize-winning scientists. Time travel has always been a fascinating subject. Many people dream of stepping into a time machine and witnessing historical events firsthand, or even altering the past to create a better future. But as intriguing as time travel sounds, It brings with it a set of complex paradoxes that make us question the very nature of reality. Today, we'll explore some of the most mind-boggling paradoxes of time travel, starting with one of the most famous, the grandfather paradox. The grandfather paradox is one of the most well-known and debated time travel paradoxes. It's sometimes referred to as the murdered grandfather paradox, but let's keep things family-friendly and focus on the core idea. Imagine you step into a time machine and travel back several decades to a time before your grandparents met. You have one goal: to prevent them from ever falling in love and having children. Why would you do this? Maybe you discovered that your grandfather played a key role in a catastrophic event. Perhaps he was a dictator, a scientist who invented a deadly weapon, or simply someone whose actions led to disastrous consequences. You believe that if you stop him from meeting your grandmother, your entire family line will disappear and the world will be a better place. But here's the problem. If you succeed, you erase your own existence. If your grandfather never has children, then your parents were never born. And if your parents were never born, then you were never born. But if you were never born, then how did you go back in time to prevent your grandfather from meeting your grandmother? It's a logical paradox. Your actions contradict your own existence. This paradox has fascinated both casual thinkers and serious scientists for decades. Some suggest that history would somehow correct itself, meaning that no matter what you do, events will unfold in a way that ensures you are still born. Others argue that attempting to change history will create an alternate timeline, a parallel universe where your grandfather never meets your grandmother, but where another version of you continues to exist in your original timeline. For example, imagine you traveled back to the early 20th century with the idea of stopping Adolf Hitler before he rose to power. Some scientists argue that even if you succeeded, history would course correct by allowing another leader to rise in his place, one who might cause just as much devastation, if not more. The grandfather paradox is just one piece of a much larger puzzle. Next, let's explore another mind-twisting paradox known as the predestination paradox. The predestination paradox takes the grandfather paradox to another level. Instead of preventing an event from happening, this paradox suggests that your actions in the past might actually be the cause of the very event you were trying to stop. Imagine that you have a close friend who dies in a tragic car accident. Heartbroken and desperate, you decide to use a time machine to travel back to that very day to save them. You rush to the scene, hoping to prevent the accident. But in your panic, you accidentally hit a pedestrian with your car, only to realize in horror that the person you hit was actually your friend. Your attempt to prevent the tragedy ended up causing it. This is the essence of the predestination paradox. No matter how hard you try to change the past, your actions are already woven into history. Instead of altering events, you simply become part of the reason they happened in the first place. This concept is beautifully illustrated in the 2002 film The Time Machine, starring Guy Pearce. The main character, Dr. Alexander Hartdagen, builds a time machine after his fiancée is tragically murdered. He believes that if he can travel to the past, he can save her. But every time he tries, she dies in a different way. Eventually, he learns a shocking truth. His desire to build a time machine only exists because of her death. If she had lived, he would have never created the time machine in the first place, meaning he could never have traveled back to save her. It's a loop that cannot be broken. This paradox suggests that some events in history might be fixed points, destined to happen no matter what. Even if you had the power to time travel, you wouldn't be able to change these moments because they are already part of the timeline. Now let's look at another paradox that takes things even further, the bootstrap paradox. The bootstrap paradox is one of the strangest paradoxes in time travel theory. It deals with something or someone that has no clear point of origin. In other words, something exists, but there is no logical explanation for where it came from. Imagine that you are 20 years old and you step into a time machine, traveling back 21 years into the past. While there, you meet a woman, fall in love, and have a child with her. A few months later, you return to the present day, completely unaware that you left a child behind. That child grows up, and when they turn 20 years old, they also discover time travel, go back 21 years, meet a woman, and have a child. Now here's the paradox. Where did the first person in this cycle come from? There is no original father. just an endless loop of events repeating over and over again. A famous example of the bootstrap paradox comes from fiction. In the Doctor Who episode Before the Flood, a character receives information from a notebook that helps him escape a dangerous situation. Later, he realizes that he only knew what to do because he had read the notebook, but the information in the notebook originally came from him. The knowledge had no true starting point. It simply existed in a loop. This paradox suggests that certain events, knowledge, or even objects can exist in time with no clear origin. It challenges our understanding of cause and effect and raises deep philosophical questions. If something is caught in a time loop, is it truly real, or is it just a quirk of time itself? Time travel paradoxes like the grandfather paradox, the predestination paradox, and the bootstrap paradox show us just how complicated changing the past could be. Even if time machines existed, these paradoxes suggest that history might be unchangeable, or that any attempts to alter it would only make things more confusing. Scientists are still debating the nature of time travel. Some theories, like the many worlds interpretation, suggest that changing the past could create alternate timelines instead of paradoxes. Others believe that time itself would simply prevent paradoxes from happening by correcting any changes. The concept of the time traveler paradox appears frequently in literature and movies. In one of the most notable examples, the American science fiction writer Robert Heinlein wrote his famous short story, All You Zombies, in the year 1959, exploring this very idea. Thanks to films like Terminator 2, this paradox has been familiar to many generations. The incident is also referred to as the ontological paradox, because ontology is a field of philosophy that looks into the nature of being and existence. Such paradoxes suggest that the past, present, and future are not fixed, which creates a tough challenge for scientists. The question arises, how can we determine the origin of something if there's a possibility that it could come from the future? This possibility isn't purely fictional, as the equations put forth by Albert Einstein show that closed time loops might actually be possible. Kip Thorne, a well-known physicist and Nobel Prize winner, was the first to demonstrate that wormholes, hypothetical portals to the past, could potentially be created under the right circumstances. This theory means that time travel could be consistent with the laws of physics. However, time travel paradoxes need to be solved, especially when they interact with experimental physics. One such example is Joseph Pinsky's time paradox. Joseph Pinsky, an American theoretical physicist, proposed a scenario in which a billiard ball is shot into a curved wormhole. Let me explain what a wormhole is. It's a theoretical structure that connects two separate points in spacetime. In Pinsky's paradox, this curved wormhole serves as a kind of time portal. The entry and exit points are very close to each other, but they exist at different moments in time. So, the ball exits from the wormhole in the past, just in time to collide with its younger self, knocking it away and preventing it from ever entering the portal. This elegant paradox offers a simple way to explore the complicated issues surrounding time travel, especially at the macroscopic scale. Pinsky cleverly avoids delving into complicated subjects like free will, the grandfather paradox, or quantum superposition, all of which tend to complicate our understanding of these strange phenomena. Instead, his idea is grounded in the laws of motion, making it a solid starting point for studying time travel paradoxes. The question now is, how might this actually work, and if it doesn't, what's the reason? Even though this paradox is speculative, it has been taken seriously by prominent physicists. For example, Kip Thorne, a renowned scientist, discusses it in his book Black Holes and Time Warps. Thorne and his colleagues have analyzed different potential outcomes of this experiment, and they conclude that while Pinsky's setup may lead to different results in each trial, there's a significant chance that the ball will always emerge from the wormhole in a way that doesn't stop itself from entering the portal. Now let's return to the grandfather paradox we mentioned earlier. Remember how we said that something always seems to stop us from drastically changing the course of events? Well, it turns out that the conclusions of speculative theories about time travel are strikingly similar to the findings of highly respected physicists. Of course, we're not claiming that everything is predestined, but we're trying to align our understanding with Kip Thorne's theories to solve these perplexing problems. Could we ever find evidence of other civilizations? Will we uncover the proof of their existence? Or is it possible that we've already stumbled upon it? For many years, humans have eagerly searched the vast expanse of space, hoping to uncover even the faintest sign that we are not alone in the universe. Equipped with the most advanced telescopes, we observe the stars and planets tirelessly, our hearts racing with the possibility of discovering something extraordinary. We listen intently, waiting for any signal that might suggest the existence of an extraterrestrial civilization. Yet, for the most part, space responds to our efforts with nothing more than the eerie silence of the cosmos, punctuated only by the distant hum of pulsars or the faint static of the cosmic microwave background radiation. But then, on August 15, 1977, something happened. For the first time in history, a signal from space was detected that was unlike anything scientists had encountered before. It was a sharp, powerful radio wave that seemed to be an unmistakable sign from beyond our planet, a clear and deliberate transmission from somewhere in the universe. This signal stood out so dramatically from the usual cosmic noise that Dr. Jerry Iman, who was part of the team at the Big Ear Radio Telescope, was compelled to take immediate action. Excitedly, he circled the strange signal on his printout with a red pen and without much thought exclaimed, "Wow!" A simple reaction that would forever be associated with one of the most perplexing mysteries in the search for extraterrestrial intelligence. The signal has since become known as the WOW signal, and it has haunted scientists, space enthusiasts, and dreamers alike for nearly 5 decades. This enigmatic event is still a subject of fascination and speculation, raising the question, could it have been a message from an alien civilization? The signal's brief yet powerful appearance has left many pondering its origin and meaning. In the summer of 1977, the search for extraterrestrial intelligence, SETI program, was in full swing. This initiative, which was directly funded by NASA, was dedicated to exploring the cosmos for signs of intelligent life beyond Earth. The program had been running for several years, and humanity's optimism about the possibility of finding evidence of extraterrestrial life was at its peak. SETI scientists had been using radio telescopes to listen for unusual signals from space, hoping to detect something that could suggest the presence of intelligent civilizations elsewhere in the universe. At the time, the Big Ear Radio Telescope, located at Ohio State University, was the primary tool used for this search. For months, the telescope had been collecting data, listening to the white noise of space, an endless static-like hum that filled the vast emptiness of the universe. Despite all their efforts, the scientists had found nothing of significance. Then, on that fateful day in August, the silence was shattered. Dr. Iman, working the night shift, was carefully monitoring the data when he noticed a strange, intense burst of radio waves. This signal was so powerful and so out of the ordinary that it immediately caught his attention. The strength of the signal was 30 times greater than anything the telescope had detected before. It was unlike any signal they had ever encountered, and it seemed to fit the exact parameters that scientists had speculated could indicate a signal from an extraterrestrial source. In that moment of discovery, Dr. Iman circled the signal and marked it with his now famous exclamation, "Wow!" That simple word would come to define this extraordinary event, which has since become one of the most famous and puzzling occurrences in the history of the SETI program. The WOW signal came from a region of space in the Sagittarius constellation, a part of the sky that had been carefully studied by astronomers. There was no doubt about the signal's origin. It came from outer space, not from any terrestrial source. However, despite the excitement surrounding this discovery, the nature of the signal remained a mystery. Was it really a message from an alien civilization? Or was it just a fluke, a random burst of radiation from some other cosmic phenomenon? The signal itself, unfortunately, did not leave behind any direct evidence of its meaning. The Big Ear Radio Telescope did not record any sounds. Its primary function was to measure the strength of the radio waves. The data that Dr. Iman circled on his printout consisted of numbers that indicated the strength of the signal. These numbers were part of a system used by the radio telescope to encode the intensity of the radio waves it detected. Most of the signals the telescope had been recording up until that point were weak, with values ranging from 1 to 3 on the scale. But the WOW signal was different. It was so strong that the scale couldn't even accommodate its full intensity, and the signal was marked with a combination of letters and numbers to reflect its extraordinary power. The WOW signal was not accompanied by any audible sound, and the data collected by the Big Ear radio telescope was not a recording of a voice or a clear message from an alien civilization. Instead, it was simply a sharp burst of radio waves that stood out against the usual background noise. Despite this, the event was significant because it was the first time that a signal of such strength had been detected, and it fit the characteristics that scientists had been searching for in their quest to find extraterrestrial intelligence. The WOW signal has since been the subject of countless analyses and theories. Some believe it could have been a form of communication from an alien civilization, while others argue that it might have been the result of some natural phenomenon that we do not yet understand. Over the years, various explanations have been proposed, ranging from the possibility of a satellite reflecting radio waves back to Earth to the idea that the signal was a result of a distant star or planet emitting unusual radiation. Despite these theories, the WOW signal remains an unexplained anomaly. No similar signal has been detected since, and efforts to find a repeat of the signal have been unsuccessful. The Big Ear radio telescope, which was once used to search for extraterrestrial signals, was decommissioned in the early 1990s, and the search for the WOW signal has continued with other radio telescopes and space-based observatories. However, the WOW signal itself remains an unresolved mystery. In the years following the discovery of the WOW signal, its fame spread, and it became a symbol of humanity's ongoing quest to understand the universe and our place within it. The recording of the signal itself, often shared on the internet, has inspired countless enthusiasts and skeptics alike who have analyzed it in great detail, attempting to decipher its meaning. Some have even slowed the recording down, trying to hear patterns or voices hidden within the noise. One such attempt involved slowing down the signal to an extreme degree. Some listeners thought they could hear a voice, perhaps even a message. In one instance, the recording was slowed down so much that it seemed to say, "We lost him at 7 p.m. We've got a 1061. This was interpreted by some as a police code for stopping a suspicious vehicle. However, this interpretation was debunked when it was revealed that the slowed-down signal was nothing more than a prank, with the audio taken from a police radio transmission and altered to sound like it came from space. The WOW signal is one of the most mysterious and discussed events in the world of radio astronomy. At its heart, it is an impressive signal that seemed to come from deep space, captured by a large radio antenna aimed towards the stars. This antenna, like others of its kind, is known as a radio telescope, which is designed to study radio waves coming from distant objects in space. These radio telescopes can vary in size, and while some may stand out against the vast backdrop of the sky, not all are perfectly functional. A key example of this is the Big Ear, which, though remarkable in its design, had a few quirks that made it less capable than other radio telescopes. The Big Ear itself was huge, comparable to the size of a football field, but its appearance made it seem unfinished, as though a larger project had been stopped halfway. Despite its size, it wasn't able to look at the whole sky at once. So how did the Big Ear manage to scan different parts of the sky? The answer lies in its design. The telescope moved along with the Earth's rotation. This allowed it to observe the same part of the sky only once every 24 hours, but only for a short 72 seconds at a time. This special observation pattern is one of the reasons why the WOW signal is exactly 72 seconds long. When the WOW signal was noticed, it followed a very clear pattern. During the first 36 seconds, the signal would grow louder and louder, reaching an amazing peak, before gradually fading during the last 36 seconds. This change in strength was a clear sign that something unusual was happening. However, the way the signal was noticed was far from exciting. Contrary to what might be imagined, Dr. Iman and his team were not watching the signal in real time like the characters in the movie Contact. Instead, Dr. Iman noticed the signal's increase only after it had already happened. Even with this delayed observation, the real challenge began when the team tried to catch the signal again. Even though the WOW signal had been recorded once, no one was able to find it again. The research team tried several follow-up observations, reaching out to other radio telescope teams for help in finding the source of the signal. Additional antennas were placed in the same part of the sky, but by the time they started their efforts, the source of the signal had disappeared. The difficult-to-find nature of the signal became clear. Despite years of trying, scientists could not repeat the conditions that led to the detection of the WOW signal. This lack of any follow-up signals only added to the mystery and fascination that surrounded it. One of the most exciting things about the WOW signal was that it was unlike anything scientists could explain using earthly methods. The signal's frequency, 1420 MHz, was especially important. This frequency was of great interest to astronomers because it is set aside for the study of signals from outer space. In fact, it is not allowed for any Earth-based communications to use this frequency. To be clear, it wasn't just avoided. It was specifically reserved for scientific research related to searching for signals from space. The use of this particular frequency is important for understanding why the WOW signal caused such excitement. In the 1950s, a group of scientists, including Bernard Oliver, Jep Coney, and Philip Morrison, proposed a theory about why this frequency was perfect for possible communication with extraterrestrial life. Their reasoning was based on the science of hydrogen. Hydrogen, the most common element in the universe, sends out radiation at this exact frequency, 1420 MHz. The idea was that if intelligent life existed elsewhere in the universe, they would probably use the same frequency to communicate. After all, hydrogen is so important to the makeup of the universe, it made sense to think that other civilizations might also recognize this frequency as a good starting point for communication. Though this idea was mostly a guess, it provided a scientific and logical base for the search for signals from extraterrestrial life. So, when the WOW signal was discovered in 1977, it was seen as a breakthrough moment in the quest to find alien life. The frequency it came from was no accident. The fact that the signal was at 1420 MHz seemed to confirm that it might be a signal sent by an intelligent civilization in space. Because of this, the frequency was set aside for future research into extraterrestrial life, making sure that no earthly communication would interfere with the detection of such signals. However, despite the promising signs of the WOW signal, efforts to track it down or capture it again were unsuccessful. Dr. Iman and his team tried hard to detect the signal again, spending several months focusing on the same area of the sky, but nothing came of it. A decade later, in the 1980s, another astronomer, Robert Gray, revisited the issue, trying to repeat the results with the latest technology. He used the meta-array at the Oak Ridge Observatory in 1987 and 1989, but again, the signal was nowhere to be found. In the mid-1990s, there was another burst of interest in the WOW signal. In July of 1995, Paul Schuck, the executive director of the SETI League, took a fresh look at the problem while testing new signal detection software. Using a 12-meter radio telescope at the National Radio Astronomy Observatory in Greenbank, West Virginia, he searched for any signs of the WOW signal. Despite the advanced equipment and his determined efforts, there was still no success. In 1995 and 1996, Robert Gray returned to the issue once again, this time using an even more sensitive tool, the Very Large Array, which was far better at detecting faint signals than the Big Ear had been. Yet despite all these efforts and all the improvements in technology, the hard-to-find WOW signal never showed up again. The mystery of the WOW signal remains unsolved to this day, with many scientists still puzzled by its sudden and unexplained appearance. What makes it so remarkable is not just the frequency it was detected at, but the fact that it came from an unknown source deep in space, with no clear earthly origin. Though many years have passed since it was first noticed, the WOW signal continues to be a source of fascination and guessing in the scientific community. For many, it represents the closest we've come to finding evidence of extraterrestrial life, yet it remains an exciting mystery that has yet to be fully explained. In 1999, astronomers Gray and Simon Ellingen tried to find a repeated version of the mysterious WOW signal using a 26-meter radio telescope at the University of Tasmania's Mount Pleasant Radio Observatory. They conducted 6 sightings, each lasting 14 hours from different nearby locations. However, despite their efforts, they never detected anything similar to the original signal. These repeated attempts only added to the doubts of skeptics. For years, these repeated failures strengthened their belief that the WOW signal was just a fluke. Skeptics struggled to come up with a convincing theory for where the signal had come from. It wasn't until 2017, nearly 50 years after the first and only time the signal was detected, that a potential explanation finally emerged. Antonio Paris, an assistant professor of astronomy and astrophysics at St. Petersburg College in Florida, suggested that the signal might have come from hydrogen clouds around two comets, 266P Christensen and 335P Gibbs. Between November 27, 2016 and February 24, 2017, around 200 studies were conducted. The results revealed that the Christensen comet emitted a noise similar to the wow signal as it approached Earth, with almost the same frequency. Further studies on other comets showed similar findings. It appeared that comets, which release hydrogen clouds stretching over millions of kilometers, could create this type of signal. Despite this theory, many astronomers remained skeptical, pointing out inconsistencies that made the theory questionable. There was no concrete alternative to explain the signal, and no new signals were detected in the same area of the sky. But then, in 2020, hope was rekindled. An amateur astronomer named Alberto Cavaliero made an exciting discovery. While studying the region of the sky where the wow when the signal was first detected, he found as many as 15 stars that could potentially be the source of the mysterious radio signal. Cavaliero proposed two ideas. First, he believed that the signal could have come from an Earth-like exoplanet orbiting a Sun-like star. Secondly, he based his hypothesis on the Drake equation, which suggested that the planet could not be closer than 500 light-years from the Sun. To compile a list of possible sources, Cavaliero turned to the Gaia telescope's database, which contained detailed information about the properties and locations of stars in our galaxy. He focused on G and K-type stars in the Sagittarius constellation. These stars had to meet certain criteria, such as having a radius between 0.83 and 1.15 times that of our Sun. To his surprise, only one star met these conditions, catalogued as 2-mass 19281982-2687. This star, with a radius of nearly the same size as the Sun's and a luminosity 1.7 times that of the Sun, seemed to be a close match. Cavaliero also identified 14 other stars in the same region that had similar temperatures, but lacked sufficient data on their luminosity and size. Still, the discovery of this one star was enough to reignite interest in the search for the wow signal's source. Since then, there haven't been any major breakthroughs, but the search for the wow signal continues. The discovery of this potential star has renewed excitement in the scientific community. One day, humanity may detect the elusive signal or find another mysterious signal altogether. When that day comes, it could lead to revolutionary discoveries on a civilization-wide scale. Recently, humanity became captivated not by a signal, but possibly by the very object we've been searching for amid the vast expanse of space. The solar system is teeming with comets and asteroids of all sizes and speeds. Every night, new ones are discovered, sometimes dozens, sometimes even hundreds. For astronomers, this has become a familiar, almost boring routine. But October 19th, 2017, was anything but ordinary. That night deprived astronomers across the world of sleep and kept them on edge for weeks. It was so unusual that they dropped everything to focus on a single, strange object in the sky. Even the orbiting observatories, Spitzer and the legendary Hubble, were directed to urgently point their lenses toward it. This object would later be named Oumuamua, which means messenger from afar or scout in Hawaiian. Now let's explore one of the most mysterious objects ever found in space, one that may hold the key to solving Fermi's paradox, the mystery of whether we are alone in the universe. But it's important to start by noting that at first, there was nothing particularly strange about Oumuamua. It was discovered not by humans, but by robots. These days, much of space observation is handled by automated systems, with several robotic telescopes working on Earth. These telescopes are the first to spot fast-moving objects, which aren't distant stars but things closer to us, such as asteroids or comets. This routine work happens every night, and over 1 million asteroids have already been detected in our solar system. On average, astronomers find 100 to 150 new objects every night, as this has been going on for decades. So when a new object was found by the Pan-STARRS robotic telescope in Hawaii, it seemed like just another typical discovery. This telescope, with a 2-meter diameter lens, spotted something that at first appeared to be a comet. Its orbit was elongated and almost parabolic, just like a comet. But then, As astronomers looked deeper, they found something startling. The object's orbit was not just elongated, it was hyperbolic. This meant that Oumuamua was not bound by the sun's gravity. It was simply passing through our solar system at incredible speed. Nothing in our solar system moves that fast. Usually objects like this either crash into the sun or get captured by it, becoming permanent satellites. But Oumuamua was doing something completely unexpected. This discovery was a huge shock. For the first time in history, we had found an object traveling into our solar system from outside of it. Until then, all the comets, asteroids, and other space debris we had seen were native to our solar system, born here and lingering for billions of years. But Oumuamua was different. It had come from beyond. Of course, this isn't entirely surprising when you think about it. Other stars have their own planets, comets, and asteroid belts, just like we do. It's likely they lose objects from their systems, just as we do. Still, it was something we had never actually witnessed before. At first, no one was sure what Oumuamua was, but as astronomers continued to observe it, they began to make new discoveries. The object was spinning, but its brightness kept fluctuating. This suggested that it had an unusual shape. Oumuamua was not a typical asteroid. It was cigar-shaped, about 35 meters wide and up to 200 meters long. This was unlike any object we had ever seen before. The initial reaction from many was that it might be an alien spaceship. But even if it wasn't, the mystery remained. Where had it come from? The trajectory of Oumuamua was tracked, and the data suggested it had arrived from the direction of the constellation Lyra. More specifically, it seemed to have come from the star Vega, which has its own planetary system. But there were doubts about this. If the object had been traveling for millions of years, the star Vega would not have been in the same position when Oumuamua passed by. The object had been discovered late, too, as it was flying in the direction of the sun. Telescopes can't easily detect objects coming from that direction because the sun blinds them. This is a major challenge when it comes to spotting dangerous asteroids. For instance, we didn't detect the Chelyabinsk meteorite until February 15, 2013, when it had already entered Earth's atmosphere and caused significant damage. Oumuamua was discovered only after it had already passed very close to the sun, inside Mercury's orbit. This in itself was unusual because no other known comets or asteroids fly so close to the sun. Oumuamua was speeding toward it at around 90 kilometers per second, a pace never before seen in our solar system. After Oumuamua completed its swing around the sun, it headed toward Earth, but by the time it passed our planet, we still hadn't noticed it. It had already passed beyond Earth's orbit when the robotic telescope finally spotted it. This was a close call. Oumuamua could have crashed into Earth without any warning, just like the Chelyabinsk meteorite. But this time we were lucky. When the unusual long shape of the object was revealed, even skeptics, those who never believed in the possibility of intelligent alien life, couldn't help but tremble with excitement. Many suggested that if it was an alien ship, perhaps we should try to communicate with it. So scientists sent a radio signal in its direction. Unfortunately, we never received a response. Afterward, we returned to considering it a natural object, though the more we analyzed it, the more questions arose. As Oumuamua flew away, it performed a strange maneuver. It seemed to use the sun's gravity to alter its trajectory and accelerate as it left our solar system. This was unlike any behavior we had seen before. Typically, objects accelerate as a result of comet-like activity, gas and dust streaming from them, but no such activity was observed in Oumuamua. This led many to wonder if it was an artificial object after all. The object's trajectory through our solar system was just as perplexing. It appeared to have originated from the direction of the solar apex, which is the point in the sky toward which our solar system is moving relative to the stars around us. This suggests that rather than Oumuamua coming toward our solar system, it might have been the solar system that collided with it, like a car hitting a pebble on the road, sending it spinning off to the side. This suggests that Oumuamua may not have been stationary in space, but rather it was on its own journey, perhaps even from another star system. There is still the issue of its unusual shape. Among all the comets and asteroids we've observed, more than 1 million, none have had this cigar-like shape. While tidal forces from a nearby star system could explain the shape, there's another theory that suggests Oumuamua's flattened, pancake-like form remains a mystery. Some believe that in order to solve Fermi's paradox, we don't need to find definitive evidence of aliens. We just need to find something that we can't explain using natural origins. Oumuamua may very well be that something. And while we may never have the answers to the questions it raised, the very fact that it exists keeps the hope alive that we might someday discover that we are not alone in the universe.